We'll give it a bit more time for people to trickle in. Meanwhile, I can get myself a coffee. Okay, let's continue. I hope the people online can hear me. Someone can just confirm. That's always reassuring.
Yes, we can hear you. I can hear you.
Okay, excellent. Thank you. Okay. Let's continue a little bit where we left off. And once we cover data structures, we can talk about algorithms, which is, of course, a little more exciting in a way. Okay, so we talked about quite a number of data structures which are part of the standard template library. So we talked about arrays, vol arrays, vectors, sets, unordered sets, maps, unordered maps, and so on, tuples. So those are, let's say, also building blocks for other more specialized data structures. And there are quite a few, which are in fact quite useful in scientific computing, although you might think, okay, that's a little bit odd. You might not have encountered a use case yet, or vice versa. You might not be aware that a certain data structure can in fact easily solve a certain problem. Okay, so these more specialized data structures are indeed often on top of other data structures. So we'll talk about a few examples of this, like for instance a stack, a queue or a priority queue, graphs, and other, well, specialized graphs such as DAGs and trees. Essentially a stack, you can view a stack as sort of a list, but you only have access to the top of the stack, so the topmost element. And before you can access other elements, you first have to remove that top element. So that's basically how it works. It is of course ordered because you have the topmost element down to the bottom. The length can vary because I can put things on the stack. I can take items from the stack. So basically, it's a dynamic data structure that can grow and shrink depending on what you put in or get out. So typical operations are push, which basically means put something on top of the stack, pop, take the top of the stack and return it, and then also peek, just have a look at the top of the stack without actually removing it. So those are your basic stack operations. The element type, as usual in C++, is in fact homogeneous. That's not a surprise. And of course, you can use this in order to model anything that is first in is last out. And you are actually using a stack data structure all the time. Because if you look at how applications are executed, applications call functions. The main function typically in C++. But the main function itself calls other functions. So basically, the execution is encoded in a stack. So the currently executing function is on top of the stack. The function that called that is below it, and so on. We go down, we go down, we go down until we get to the main function, which is of course always at the end of the day the calling function. And this is a data structure that is really built in memory at the moment your application is executing. So that is one example of where stack is useful. So one application in scientific computing is that you emulate this in a way in order to make a recursive function into an iterative application. A relatively easy way to do that is to use a stack in order to emulate the function calls. So that would be one example of using a stack in programming in general, but yeah, that's also something that you from time to time need to do in scientific computing. Okay, so basically there is an implementation of a stack in the STL. So you don't have to do that yourself, it's just there. And here's an example. So as usual, we have an include. So we include stack. We create a new stack instance, and then we specify the elements, the type of the elements. In this case, we put integers on the stack. Okay. We do that using the push method. Takes an integer, and then of course it's a container, so we can ask whether it's empty or not. So as long as it's not empty, we can simply look at the top of the stack and then pop it. So the peak in C++ peak is actually top, but it's the same thing. You just have a look at whatever is at the top of the stack without, in fact, removing it. So it's a two-step operation if you want. If you want to use the value at the top of the stack, you use the top method, and then you pop the value. Okay, so this is different, for instance, from Python's implementation of pop, which actually returns whatever you removed from the list or whatever your data structure is. Okay, another another data structure that can be quite useful is a queue. And in a way, a queue is a bit similar to a stack. Only what you do is you exit it from both ends. And depending on the particular implementation of the queue, you actually remove from the front and add to the back. That's typically how a queue works. There are implementations that allow you to also insert at the front or remove from the back, but your typical implementation says, okay, add stuff to the back, remove it from the front. And of course, if you think of a real life example, that would be what happens at the checkout in a store, that basically you queue. The first one in the queue is the first one to pay, and if you arrive at the queue, you stand in the back and you wait until it's your turn. So essentially, this is the data structure which you could use to model that. It's also ordered, of course, because someone is at the front of the queue, someone is at the end of the queue, and basically it's an ordered thing. It's especially ordered in the UK, but also in Europe, we actually try to implement the concept from time to time. Okay, again, just as with a stack, the length of a queue can vary. So I can add, well, push things to the end of the queue, pop things from the start of the queue. So it's dynamic, and these are typically very fast operations. As usual, all the same elements, no surprise there. And this is, of course, first in, first out. So stack was first in, last out. Queue is first in, first out. So queues can be quite useful as well in scientific programming. For instance, if you have a system that, for instance, selects a number of particles that should be moved in an MD simulation or something like that, then basically you could add them to a queue and then iterate over the queue. That might trigger other particles to be updated. They go to the back of the queue, etc., etc. So that would be a possible application of queues in scientific computing. So they are used quite regularly, let's put it that way, and in probably unexpected places as well. Okay, again, there is an implementation of a queue in the STL. Here's again an example. We store integers in our queue, then we push, and rather than using top as for a stack, we use front, because that gives us the first element in the queue. And of course, front is defined for most STL containers to give you the first element, whatever first is. And then you use the pop operation to remove the first element. So very, very similar to a queue, to a stack. Of course, the semantics is different and the use cases are different. Okay. Another interesting data structure is sort of a queue, but a special one, a priority queue. So basically, again, you add things to the queue, but they don't go necessarily at the end of the queue. So depending on some priority computation, they can end up somewhere in the middle, or even at the front of the queue. So that depends on priority. So basically, like before, for an ordinary queue, you use the front is always the element which you pop, so that doesn't change. Only where a new element enters the queue, that is open. So basically, again, of course, the length can vary. That is pretty obvious. Okay. Basically, removing an element from the queue, so taking the first element, that's cheap. But adding something to a priority queue, of course, is a bit more expensive, because at the end of the day, you need to put it in the right place. So that means you need to do some computations in order to assess where it should go. You should evaluate its priority and then compare it to the priority of stuff that's already in the queue in order to insert it in the correct place. So don't use a priority queue if you don't need it. If you just need an ordinary queue, use that because this is more sophisticated, hence more expensive. So yeah, you pay for, in that case, you pay for functionality you don't use. That's of course a bad idea. Okay, so again, it's in the STL. It's of course again a data structure which is used quite often. Also in, okay, maybe not quite often, but also used in scientific computing. For instance, one of the applications which comes to mind is basically one which also had to do with a simulation where it was a lattice, a particle simulation where particles moved on a grid, and depending on certain circumstances, they had a higher or lower probability to move in the next update. And so basically implementing this using a priority queue was actually quite fast. So that would be one example. Another example of using a priority queue, which may be a little bit unexpected, is that you can use it in order to compute the running median for a set of values. So basically, values arrive in a streaming fashion, so one after the other, and at any given time, you want to be able to determine the median. And you want to do that fast. So one way to do that is to use two priority queues, so that in fact your elements are ordered and that the median is always either the top of the queue of one of the two queues, depending on how you define them exactly, but one of the two, or if there is an even number of elements, simply the average of the top of the two queues. That's basically the idea. So that's another implementation which is not necessarily directly related to physical sciences, but if you're in mathematics, then that's a nice application as well. Okay. A very general data structure, which is useful in many domains, is a graph. And a graph consists of nodes. And those nodes can or cannot be connected with vertices, with edges, sorry. Nodes or vertices, and they get connected with edges. These edges can be either directed or undirected. So basically, if they're represented by an arrow, that means that, for instance, this guy here is connected to that guy, but this guy is not connected to the other guy. So that would be a directed graph. If there were no arrows, then it would be symmetric. If vertex A is connected to vertex B, in an undirected graph, vertex B is connected to vertex A. So that's a mathematical distinction which you make depending on the type of your graph. Okay, so in a certain way, it's an ordered data structure in a sense if you have a directed graph, because a vertex has an outgoing edge, so that implies sort of a direction, sort of an order. You can define transitivity on that if A is connected to B, and there's an edge from B to C, then indeed A and C are also connected. There is not an edge between them as such, but using the transitive closure, you can get there. It's reachable. Okay. And for undirected graphs, you could say, okay, they are sort of unordered because there is no direction in the connectivity. And of course, it can be a dynamic data structure in the sense that you can add vertices, you can remove vertices from a graph. You can add edges, you can remove edges. Basically, it's a very dynamic thing. What you can do with certain, well, with all decent implementations, is you can add information to vertices on the one hand, properties of something, and you can do the same for edges. So to give you a real-world example, which sorry, you're all familiar with, is a social network. So you can represent a social network using a directed graph, in the sense that all the members of your social network are vertices, and if I'm a friend with someone else, then basically that would mean typically it's mutual. So essentially there would be an edge between person A and person B, and an edge between person B and person A. In some social networks, for instance, if I follow someone, that relation, an edge of that type, would be directed, and it could be that A follows B, but B does not follow A. So essentially you see that it's very easy to represent a social network using graphs. And then of course, what would be annotation, what would be data? Well, for vertices, of course, they would refer to members. So you would have information such as the name, depending on the social media platform, whatever information you share about yourself, or the platform can figure out about you, depending on the platform. While information on the edges could be the type of the relationship. So for instance, being a friend or following, things like that. Okay, so that's a very easy example of where that would come in let's say, I hesitate to call that real world because calling social networks real world is maybe a bit a bit controversial, let's put it that way, luckily. But in science, scientific computing, if you don't do that kind of analysis of networks and so on, it also comes in. For instance, if you do a domain decomposition, which is, okay, if it's trivial, then you still have a graph, but you typically represent it in a different way. But if you have a really non-trivial domain decomposition, where the decomposition is not just a cube or something like that, or a parallelogram or something like that, then basically you need to somehow encode the information that part of your domain A is a direct neighbor of part of your domain B, because they need to exchange information at some point, because otherwise, yeah, what are you going to compute? And that information can be stored in a graph. And for instance, if you look at MPI, so the message passing interface library, you will see that there is a communicator that can represent graphs, graph-like structures. It's not the fastest thing around, so if you don't need it, please don't use it. But again, it's there, and it has obviously its uses, especially in the case I mentioned. But there are many other applications of graphs in computer science, but also in mathematics, obviously. Any system you want to analyze, basically, at the end of the day, boils down to graphs. Okay. So there are a number of ways to represent graphs. For instance, you can have an adjacency list, which says, okay, there is an edge between A and B, and there is an edge between C and B, and so on. That would be an adjacency list. That's one way to represent them. There are other ways to represent them. That is not a point. So one place to look for an implementation is the Boost library. So it has a graph sub-package, which is interesting. My only quibble with it is that I truly hate the documentation. okay, I'm not happy with it. Let's phrase it that way. Okay. I think there is an example in the. I would have to check, but I think there is an example somewhere in the repository. Okay. So of course, we have on the one hand general graphs. Anything can be connected to anything, but there are also more specialized graphs which are quite useful. For instance, directed acyclic graphs, which basically means you have a directed graph, as the name implies. So edges are one way from A to B, does not imply B to A. And for a DAG, there shouldn't be cycles. So basically, A to B to C to A would entail a cycle. That's a bin. Then it's not an acyclic graph. Okay. Why do we care? Because acyclic graphs are really, really nice. It's something that you, again, use all the time without perhaps realizing it, but you use it all the time. Because if you use any software build system, your dependencies between your different components are in fact encoded in a DAG, in a direct acyclic graph. So build systems do that. Also, if you, for instance, use something like Dask in Python for distributed computing, for executing tasks in parallel, computations in Dask are in fact also encoded before they get executed. They're encoded into a direct acyclic graph. So you are actually using them all the time without even realizing it, maybe. Okay. So this guy here would be indeed a DAG. Note that, of course, there can also be vertices that don't have any incoming or outgoing edges. That's the case for all graphs, but yeah, just to show you that that's the case. And as you can see, there is no cycle here, because there's no way, if I start in this vertex, that I can get back to that. And that goes for all nodes, for all vertices. So basically, this is a direct acyclic graph. Okay. And even, another, by the way, another application of direct acyclic graphs in languages that support multiple inheritance, that's a DAG as well. So, in other words, C++ inheritance, in fact, is a DAG at the end of the day. If it's not, it won't compile. So basically, that is what it is. In languages that don't support multiple inheritance, of course, that would not be the case. In that case, you would have a tree, and basically, a tree is characterized by the fact that a vertex has at most one incoming edge. That's it. So basically, you have a special node, typically, which you call the root, and then it has outgoing arrows typically to its children. Those have outgoing edges to its children, and so on. But there's only one incoming edge per node, and that's essentially the idea. And trees, of course, occur quite a lot. One application of trees, for instance, is if you do if you want a good search structure for querying spatial data based on coordinates, then essentially a tree structure is your friend, either a quad tree or whatever. But basically, what you would do is you would decompose your spatial domain into a tree structure of smaller and smaller areas or regions in that spatial domain. So that's one example of using a tree-like structure, or tree structure essentially, in scientific computing. Okay, that's the data structure. There are lots of algorithms on graphs. So for instance, MaxFlow, essentially that's something that comes from systems that transport stuff, and you want to know what the maximum flow is. So how much can you get at most from point A to point B, given restrictions on the edges with respect to, let's say, their bandwidth, or however you want to call that. Of course, the original idea was, let's have a look at river networks, for instance, how much water can go from A to B. That's one example. Another very important example is shortest path. So basically you want to know the least amount of edges you need to cross to get from A to B. Or if your graphs have weight, so essentially if the edges have weight, what is the path which has the least accumulated weight? So that would be another very useful graph algorithm. And then in D graphs, so directed graphs, topological sort is of course interesting, because then that has to do with, for instance, our build system. It needs to know what to build. So basically you need a sort of your data structure in order to know what to start with in order to get your build done. So basically in this case, we have this particular graph, and the topological sort would be this guy here. Okay. And in this case, of course, since there is one vertex that's not connected, essentially I can have quite a number of topological sorts, because it's only there is only an order on A, B, C, and D as such. Okay. Of course, this is not unique. I can have multiple topological sorts for this particular graph. Okay, so again, as usual, there is a corresponding chapter in Starstrup's book, his tour of modern C++. A number of things were added in this case. So we discussed value arrays, so these val arrays, which can be useful in scientific computing, because they support your elementary operations on arrays, such as adding a scalar, doing an element-wise addition, and so on. So all of that is supported on val arrays. So I consider that potentially a useful data type for scientific computing. So for some reason, Starstrup discusses tuples in another chapter. There's undoubtedly a very good reason for it, but I forgot what it is. But I decided to put it into the data structure thing. He doesn't talk about sets, he doesn't talk about stacks, queues, and priority queues, and graphs. So basically, I decided to add that because those are very useful data structures in our specific context. Okay, let's see. The next topic builds on the previous one. So essentially, what we want to do is we want to do stuff with containers, stuff with vectors, stuff with lists, and so on. And very often things are quite similar that we want to do to those. For instance, I might want to sort the elements in a container according to some criterion. Another thing I might want to do is to find something in a container, find a certain element, or find all the elements for which a certain predicate is true. So all these kind of operations are typically defined or desirable on all containers. Now, the problem is that the implementation is of course going to be container specific. I will search differently in some data structures, or I'll write a different search algorithm in certain data structures. And in some data structures, I can get a very efficient algorithm. For other data structures, that algorithm will be, not that fast, but still, you get a good implementation if the implementers of the standard template library have done a reasonable job, which typically they did. Especially for the older algorithms, they have been around for quite a while, so people have had time to optimize them. So basically, that's quite good. It's a whole zoo of algorithms, and I think it's a very good idea to just have a look at the documentation and see what's out there. So let's maybe just do that. And I don't think I mentioned at this point my favorite documentation page for C++. So let's take the opportunity to do that. If I can get this window resized. Okay, why am I bothering if I have a mouse here? This is stupid. Okay, CPP reference. So this is really a very nice website in many respects. It's a reference site. So basically, if you know your way around C++, this is really a very good source of information. Of course, it's reference, it's not a tutorial. Okay. However, for each, let's say, concept or each data structure, each algorithm, you do get examples. So it's a little bit a tutorial, but at a low level. You already need to know what's in there, more or less, before you can use this effectively. So one of the things I do from time to time is go through this and see, okay, this section, I'm not that familiar with it. Let's have a look. What's in there? And of course, I will not remember the details, but that doesn't matter. As long as I have some idea that something is in the CPP reference, so essentially in the standard template library, I know where to look for it and I can find it very easily. So basically, let's go down to algorithms. Here you see the container library. So as you can see, we talked about quite a lot of these guys. So basically, almost all of them. We will talk about span later on. That's also a useful one. So what I also like about it is that if something is introduced in a certain specification of C++, that's also clearly indicated. So as you can see, there is stuff in there that's been there since C++ 11, but there is also stuff that has been added more recently. For instance, a span was added in C++ 20, and MD span was added in C++ 23. So you immediately see, is this relevant for me at this point in time or not? Because typically when you do development, you think up front, okay, which specification am I expecting that the compilers that will compile my code when it gets installed, wherever, what are my minimum expectations? So do you expect C++ 17? Do you expect C++ 20? Okay, if those are your expectations, then of course don't use features of higher specifications. So if you say, okay, my baseline is C++ 20, I expect all containers that build my software to use C++ 20 or to support C++ 20, yeah, then don't even bother looking at the C++ 23 stuff, unless it's for release later on when you say, okay, change my mind, now it's going to be C++ 23. Too bad for you. So, but again, in HPC, We are typically somewhat conservative because on many systems, compilers are not the very, very latest generation. Typically, we prefer maturity over features which are maybe not that well implemented or not that stable. So typically, we're a bit conservative. So keep that in mind if you develop software, that the latest, shiniest might not be easy to install on HPC systems that could give trouble. Okay, but the problem is that even if you see, for instance, that MD-SPAN was introduced in C++ 23, that's great. Unfortunately, there's, as far as I know, no compiler you'd use on HPC that supports MD-SPAN at this point in time. It's 2025, last time I checked my calendar. So yeah, that is somewhat annoying. It's especially annoying for us because the MD in SPAN stands for multidimensional. So this is a way to create multidimensional views on one-dimensional data. That's something we do a lot. It's called arrays, multidimensional arrays. So there is support for that concept in C++ 23, and hopefully compiler makers will at some point add it to their bloody implementation, because this is frustrating me. I really want that. Anyway, so basically, that's how you should read this. You can see that there is even already stuff for C++ 26. Okay? If you have, let's say, alpha versions of compilers, some of that might be supported by some compilers, not by others. So stay away from it because that is really not a good idea. Okay. Algorithms. Let's have a look. Because that was what we were actually here for. Not for me ranting about C++ versions, although that's useful. Okay, so there are quite a number of categories of containers. So let's not talk about ranges now, we'll talk about ranges later. Let's go not talk about execution policies, that's for another training. But here are some interesting operations. So for instance, there is a for each algorithm. And essentially what it does is it takes a container, an iterable, and it will apply a function to each member of that container. Okay, so that is quite useful because that's something that you might want to do on a regular basis. So there are some variants. So for instance, you can restrict that to the first n elements. Yeah, that's very interesting. So that's one type of algorithm. There are also search operations, as you can see. And there is, for instance, all of. So basically, it will check whether a certain predicate, so Boolean, an expression, well, a function that returns a Boolean, is true for each element in that iterable. If that reminds you of Python's all function, yeah, it does a similar thing. And then, of course, you have any of, you have none of, etc., etc. So basically, the whole range of that type of functions which you would expect. Okay, find, yes, find a certain element in a container. Find it if a certain Boolean function returns true. So if there is a predicate that returns true. Find if not, same thing, but negation. Find and blah blah blah, find first of, etc., etc. As you can see, there is quite a number of these algorithms. Count, also quite useful. How many elements have a certain predicate to be true? Count if. So there are as you can see, quite a lot. Equality tests. If I have two containers, are they the same? So you get an element-wise comparison. Search, etc. Search n, blah blah blah. So all kinds of functions here. Again, a different type of operation. So fold operations. That's basically sort of okay. A simple fold operation is a reduction. So essentially, you compute the sum of the elements. How do you do that? You have a starting value, and then you use the last element of that data structure and you add it. That's your current sum. You add the one before last, etc., etc. So it'll be a fold, and you can either fold from the left or fold from the right. And there are two of those. So basically, that is also a very common operation. There are more specialized operations for this as well, by the way. We'll counter those later. Copying, also interesting. Copy under certain conditions, etc., etc. Swap operations. Then also a general transform. So that is also possible. A replace if, fill, generate, etc. To remove things. Sorting operations, including reversing, rotating, and so on. Random shuffle, also a very interesting one. Sampling, also quite useful from time to time. So as you can see, there is a very wide range of algorithms that are implemented. And of course, the nice thing is they will work on many containers as long as it makes some sort of sense. So that is, yeah.
Is there also some information on how efficient each of these algorithms is? And if it depends on which type of container?
Yes, it will critically depend on the type of container, and I can give you a trivial example. So, for instance, suppose that you want to find very simple operation. You want to find the first element in a container that is equal to some given value. So, for instance, my container stores integers, and I'm using container in the very broad sense. It can be anything, essentially. So I store integers, and I'm looking whether there is a 0 in there or not. Okay. So if my container is a vector, what can I do? I don't have much choice here. The only thing I can do is go through my container element by element, and as soon as I find an integer element that's equal to 0, I stop and I say, okay, here it is. That's all I can do. I cannot be smarter. Yeah, I can do that in parallel, but that's a different thing. Let's, for the moment, assume sequential operations. Okay, now on the other hand, that would be the same for a list. You don't have a choice, you have just to go through it, and yeah. So the complexity of that thing is, of course, O(n), where n is the length of the list. In worst case, if my search element is, if my search value is not in the list, I have to traverse the whole thing. So I need to do as many comparisons as there are elements in the list in worst case. Can't help it, nothing to do about it. On the other hand, if I use a set, things get a lot more interesting, because the set in the STL is in fact it's sorted. So basically, what I can do is say, well, okay, I'm looking for a certain value. All right, I'm going to look in the middle. If the value I'm searching for is less than the value I find there, I'm going to search in the first half. Otherwise, I'm going to search in the second half. So each time, I'm going to divide the data I'm looking for into two parts. So, of course, that gives rise to a tree. First half, second half of first half of second half of first half, etc., etc. So you get a tree. If you have a tree and things are balanced, then essentially the height of the tree is going to be the logarithm of the number of leaves in the tree. The number of leaves in the tree is your number of elements in your set. So basically, I have to do log n comparisons. So find on set would be log n, O log n. That's worst case. Okay. Now, on the other hand, we also have unordered set. Unordered set works differently. Unordered set uses hashing. Okay, so what happens? You have an element and sort of an index, a key is computed, and it's checked whether that key is in the set data structure or not. That's a very fast operation. Okay, if it's there, you need to do something more. You need to check whether the value is actually associated with it or not. Because internally, it might be that a key maps to multiple values. So don't confuse this with a map. This is low level. This is something else. So basically, it might mean that you need to do multiple comparisons, but still quite few. So if you don't have too many collisions, it's called a collision. If a hash value of two different values give the same key, if you don't have too many collisions, then it's more or less O1. It's essentially O size of the bucket associated to a key, to be very precise. But yeah, that's a small number compared to n. Question in the chat. Okay, I will reshare, but normally I'm sharing. So I'll stop sharing now and I'll share again. Just to make sure, but normally that was okay. I'm sharing also my entire screen, so you should be able to see whatever I see. So let's do that again. Okay. All right. So basically, that would be ON. So yes, it critically the performance of the same quote unquote, it's not the same, but of what we call the same algorithm find, critically depends on which container you apply to. Yeah. And that goes for many algorithms, because some containers have special properties like a set which is ordered. Well, okay, no, let's rephrase that, which is sorted. So that helps because that allows you to do things faster.
And is it the information somewhere, or is it something you should know yourself?
Well, basically, you find it typically in books about algorithms, that's for sure. Let's check whether there is something here in... I doubt it a little bit, to be honest. But let's see. Let's take the find example, for instance. Just a simple find would do. So this is not it. Parameters is not it. Type arguments won't be it. Complexity, yes. So basically, there is at least, let's put it, there is at least a section about complexity, but yeah, it's not that extensive, let's put it that way, because it just gives at most, and yes, that's of course true, but again, that won't be happening for a set or an unordered set. So this only gives the worst case for the worst possible container. So it's not very helpful, unfortunately. I understand why they do it this way, because if you have to, for each algorithm, really specify the complexity for each data type, that means that you are also imposing an implementation. And in a way, I'm free as an implementer of the STL. I'm 100% at liberty to say, okay, I'm going to implement find for a set by just iterating over each bloody element and looking whether it's there or not. I can do that. But this specifies a bare minimum. Of course, if I were to release an STL implementation that would do such stupid things, yeah, then it would not, hopefully not be very successful. So this is a little bit Darwin here at work, but yeah. So yeah, there is information, but it's really worst case. For worst case container, for worst case search, for worst case whatever. So yeah. Okay. So there is a lot. Again, it's a very good idea to just go, yeah, a question?
Yeah, so let's follow up on that. So
yeah.
The functions or the algorithms that are mentioned there, like find and so on, they seem very generic for any type of function.
Correct.
So does it determine then on compile time which type of find
exactly.
you take depending on? Yes, it does.
Yes. So basically the question is, this looks really generic. So how on earth can a specific good, quote unquote, an appropriate implementation of this algorithm be devised? So that's runtime, that's compile time information. So the compiler is going to have a look at your code, and it sees that you are applying find to a set of integers. Let's just take that as an example. Okay, somewhere in the STL, there is a definition that says, well, okay, find with as an argument set. Okay, that's the algorithm which we're going to use in this case. And there will be another template where it says, well, okay, if you call this thing with a vector, then this is the implementation which we will use. So that's called template specialization, and that is something that is pervasive in the standard template library. And that's, at the end of the day, why it's called the standard template library. It's all template based, so all the selection of the algorithms happens at compile time. So that's cheap. Well, cheap in the sense that it will sometimes blow up your compilation time and compilation requirements sky high. That's a different discussion. But at runtime, it's for free. And that's the power of the C++ standard template library, that you pay for it at compile time, but at runtime, it's cheap. So that's the big selling point of this, the nice design of template and generic programming. Okay. So that's all very nice, but how the hell do we use that? So let's go through some things we need and some examples. Okay, so the first thing we need, and we need to understand when we talk about algorithms, because they're all based on those things, that is in fact the concept of iterators. And those of you who are into Python know iterables, so that's something that you can iterate over. So basically you get the elements of the thing or whatever it produces as a sequence of values. And essentially C++ has a similar concept. Again, it's not something in the language, it's something that's provided by typically the STL, or that if you want, you can program yourself as well. So let's just consider a vector here, and the elements are double. and I initialize it to, what is it, 5 values, something like that. And we typically iterate over that up to this point using a range 4. So for auto reference value in vector, okay, no, in column vector, do something with value. And of course, that's a very elegant way of writing code. It's a modern way of writing C++, introduced in, if memory serves, C+17. So basically, it's a very nice way of programming. The older way, but which is still in some circumstances quite useful, is by using iterators. And each container actually has a function to get 2 special iterators, the begin iterator and the end iterator. Okay? So this is a classic for loop. We have initialization, and I'm initializing IT, which stands for iterator. I'm initializing that to have the begin iterator of V. Okay. Then the second part of my classic for loop is a Boolean expression. So I continue the next iterations of my for loop as long as that iterator is not equal to V's end iterator, to the end iterator of the vector. Okay. And then, as usual, I go through the loop. Let's discuss that in a minute. And then at the end of the loop, I'm going to update my iteration variable. So in this case, I'm going to update the iterator. I can update that by just doing ++ iterator. I could do iterator ++, but this is why I mentioned somewhere in the very first session, it's better practice just to make it a habit to write ++I or ++ iterator, because there can be performance issues with iterator ++. So that was why that remark was there, and this is the justification for it. So in some circumstances, you might have inadvertently copies here, which you don't want. So that's why pre-increment for iteration-based loops is the way to go. And that's why I just make it a habit myself. You don't see that much in code on the internet, but it's my personal habit to, for each classic for loop, to just use ++ for the iteration variable, so the pre-increment, just to make sure I don't accidentally mess up here. Just always the same thing. It minimizes thinking. The least I need to think about fussy details like that, the more I can think about other things, like trying not to mess up in my implementation. So, just a habit. Okay, so we're nearly done. The only thing which I glossed over was the iteration itself. Now, how can we use the value? Well, you can view iterator as sort of a pointer to an element in that vector. And to get the value, we need to use an operator. So this is the value of operator, and that works on that iterator. So rather than whatever it points to, which is an abstract thing for us, because I declare this thing auto, so we don't care what it is. We know it's an iterator. Apart from that, we don't give a damn. So essentially, if we want the value that an iterator points to, we just use the star operator. So this is another use of the star operator. As you know, many programming languages reuse operators. A very simple example is you can use a dash as the minus sign. You can also use it as the subtraction operator. Either it is a unary operator or it is a binary operator. Same thing here. The star can act as a binary operator, and then it's usually the multiplication of stuff, or it can act as a unary operator, and then it is value of. So in this case, it means give me the value that the iterator at this point points to. Sorry for the feeble pen. Okay, so we can represent that graphically, which is probably a good thing to do. So v begin, I'll come back to what the C does there in a second. You probably already guessed, but let's gloss over it again for now. So v begin points to the first element of our vector. Okay. V end points to, maybe surprisingly, not the last element, but rather the quote-unquote element beyond that. So kind of a spooky element that isn't there. That's beyond the end of our container, in this case our vector. So that's how you can visualize this. Okay, so iterator will simply, during the for loop, go over each element until it reaches v end, and that signifies, okay, now it points beyond the values that are in this container. So this is essentially how it works. Okay. So in a way, it need not be that way, but you can sort of think of it as if the iterator contains the address of wherever the element of the container happens to be in memory. You can view it that way. It's not quite true. It's not a row pointer. It's an iterator. It's an object. But semantically, that's what it is. It's kind of an address of there's the data. Go and look for it. How do you go and look for it? You just apply the binary value of operator, the unary value of operator. So this, the asterisk. Sorry. Okay. So let's apply that in the context of algorithms. And one of the algorithms which can be useful is a sort. So we include algorithm. That's of course the first thing to do. We create again a vector. And then we use the sort algorithm. So it just takes 2 arguments, at least. And the first argument is the begin iterator of the container we want to sort, and the second is the end iterator of what we want to sort. That's all we need to do. Then things are sorted in ascending order, where the order is defined by the data types of the element. And for trivial stuff, it works out of the box. So basically, if you have a vector of double precision values or single precision values, integers, characters, whatever, strings, they will just be sorted according to the natural sort order of that particular data type. Easy. Okay, of course, it's also possible to provide your own search predicates, so that basically you can define a sort order. That's also quite possible. And then you do that by supplying a third optional argument that overrides the default sorting behavior. Okay, and then basically you can just write all the elements of this vector as they're now sorted. So this is of course an in-place operation. And the eagle-eyed among you might have noticed that I use begin and end here, and that on the previous slide I used C begin and C end. You can now probably guess what's the distinction. So C begin and C end are constant iterators. I'm not going to change my elements in my container in any way. While with begin and end, I'm at liberty to do that. Now, a sort algorithm is going to change the elements in my data structure. It's going to reorder them. So, of course, it cannot take a const iterator, because then I'm trying to change something that is declared as constant, and of course the compiler is going to refuse that. So that's why there is a begin and an end here. While on the next line in the for loop, it's again a C begin and a C end, because when I'm just printing out the values, yeah, I'm not going to change the values. So I can happily use C begin, C end, and ensure that I can't change the value which IT points to. Okay. All right. So basically, that's explained here. So the usual advice is valid. If you know that your algorithm is not going to modify the container, use C begin, C end. It's just making very clear that that is not happening. Compiler figures it out anyway. That's not an issue. But for yourself, it's a visual reminder that nothing is going to change. Okay. Then suppose indeed that you don't want the default. Yeah.
Question on the question about the previous
Okay.
Algorithm.
Yeah.
Here, the auto iterator is passed by reference, I guess.
Yes.
And in the previous slide,
It wasn't.
it was not as a real
Yeah.
type or just
No. It's better to do it by reference actually. But yeah, in this case it's cheap because yeah, I am making a copy of that. I am in fact making a copy of that iterator at that point, unless I declare auto reference. Now, yeah, making a copy of this particular iterator, it's very cheap. Now, on the other hand, if I have a data structure or container, which I define myself, for instance, and which has a relatively heavy implementation of, on the one hand, begin, end, and the increment operator, yeah, then I have to be a little bit careful, because then making a copy might be an expensive thing to do. So it depends. So yeah, in fact, it would be better if I updated the previous slide to also use autoref rather than auto itself. It's again one of these things that's good to have the habit of, just type it anyway, rather than having to think, should I do it here? No, just do it. It's the same with the range form. So in general, you assign to autoref, even if you don't intend to change anything. If you don't intend to change anything, just declare it const. So it's the same reasoning. Just do it because, yeah, it requires less thinking. It will, as far as I know, never hurt. And the advantage is that if it were to hurt to forget it, you do it automatically and you don't forget it. Same thing. Okay, but there was also a question in the chat, I think. Why is it by reference? Yeah, so essentially, same question. So essentially, what I'm saying is that with autoref, it basically means that the result of cbegin is actually going to be a reference to whatever the begin function or cbegin function returned. Yeah. Okay. So basically, we have our data structure, and in this case, it's a little bit less trivial. So it's a struct, nothing fancy. You can make this object, I don't care. But basically, I just want to show it as a struct. It has 3 members or 3 attributes: y, x, y, and mass, and all of them are double. So nothing fancy. And then I can make a vector of such particles. Assuming that I have some function which is happily going to return a vector, which is initialized with some number of particles, which I specified here. So this is defined somewhere else. It lives, it thrives, it's very happy. It's of course something you write yourself. Okay, and then the question is, how do I solve this? Because now in this case there is no easy way or no trivial way to sort this. You can think of one. You could say, okay, first going to sort on the first attribute. If those are equal, I'm going to sort on the second attribute. If those are equal, I'm going to sort on the third attribute. So you could do something like that. But of course, that has fairly little value because likely that doesn't make any sense anyway. So you want to define your own sort order. And in that case, what you can do is you write a predicate. And that predicate, that was not my intention. No. That predicate actually takes two elements. Let's call it that. In this case, of course, they're particles. We don't want copies, so hence the ref. We're not going to change, hence the const. So we've got our two particles P1 and P2, and then we return true if particle 1 comes before particle 2 in the order which we want to define. So in this particular case, this would sort on the mass. This is of course not a total order, it's a partial order, because nobody knows what happens if two particles have the exact same mass. Then it's undefined which particle is going to be the first one, which is going to be the second one. So yeah, just keep in mind, this is a partial order, not a total order. Okay, and then we can sort on mass, and as I already mentioned, the only thing you need to do is to pass an optional third argument, which then is the predicate that says, okay, this is what it means to be less than for two particles, one being less than the other. That's what you do. Okay. If I wanted to make this a little more total, one of the things I could do is say, well, okay, if I have two particles and they would have, they would not, the mass would not be smaller, okay. In the else case, I'm going, for instance, just making something up, compare the distance of these particles to the origin. And then the one which is closest to the origin, I'm going to consider the smaller one. Okay. My order would be a bit more total, but still not total, because any two particles that are the same distance from the origin would then again have no order defined on them. So yeah. Can you make a good total order here? Maybe. I don't know. If it makes sense for you, no problem. But that's up to you as a programmer. But of course, if you use a sort algorithm with a partial order relation, then of course you have to realize that results might not be identical when you switch implementations. So from one C++ version to the next, you might get a different order, because the order is not total. Just something to keep in mind. And yes, this leads to retractions of hundreds of articles in scientific journals, by the way, because someone relied on the fact that if you get file names out of a directory with a certain Python library, they would always appear in the same order, and the application relied on that order. Very unfortunate, but depending on your operating system and hence the Python implementation, you got something else. So quite a lot of publications had to be retracted because the results turned out to be either not entirely reliable or unfortunately taken into an expensive random number generator. So that's why I'm mentioning these kind of things. It's not trivial in all circumstances. Okay. Why do we use begin here? In this particular case, I'm going to modify my container. I'm going to reorder the elements in my container, so I can't make it const. I can't do C begin, C end, because sort is going to modify my container. So that's why I should do that. Yeah, and actually Maximilian gave the answer, so yeah, indeed. Sorry, I was reading top to bottom, but the question was indeed already answered in the chat. Okay. So another example is a predicate find. So a simple find is easy. Just look for value. That's it. Very easy. A predicate find is, of course, a bit more interesting. So basically, what we do is we use the find if algorithm. Then we specify cBegin, cEnd on our container. Again, finding is not going to modify anything, so I can use cBegin, cEnd and should do so. Okay, and then we have a lambda function. And that lambda function should return true when we found what we're looking for. It should return false otherwise. Okay. So let's have a look at the lambda function. That is the body of the lambda function. So essentially, x is going to be the argument, and I'm going to check whether x is negative. If x is negative, I return true. If x is positive or 0, then I return false. We did discuss lambda functions, yes? Because I can't quite remember. Problem is, I'm also teaching to students, and in the same period, and it gets confusing after a while what I discussed where. So this is getting interesting. Okay, so this is a lambda function. We don't need to capture anything in this case. If we want to, we can. So we can do sophisticated stuff here, but we don't need to. So empty capture, and this returns true. Okay, so that's our function that's our find if algorithm. On the one hand, begin iterator, end iterator, and then our predicate as a Boolean function. Okay, so now there are two options. Either find if we finds the value and returns an iterator, or it doesn't. If it doesn't find the value, what it's going to do is return the end iterator. Hence, the if find if, and we compare the result to data cEnd. Okay, so if find if finds something, then the resulting iterator will point to that, and it's not going to be the end iterator of the data structure. On the other hand, if it doesn't find anything, it is going to return the end iterator of the data structure, and then of course the if statement here would not be executed. So we only print that we found it if indeed we found something. Okay. Now you might wonder why all these shenanigans are necessary. Because just think of the sort algorithm. Why do I need to go to the trouble to specify the begin iterator and the end iterator? Why can't I just plug in data and have the sort algorithm figure out what the begin and the end iterator is? I mean, just 2 extra function calls. So what's the problem here? Okay. Any ideas why this design was chosen? That you always specify the begin and the end operator. Sorry, iterator, not operator. Why would that be helpful rather than more typing, boring?
Sort of, you can sort or find in only part.
Yes.
Of the data.
Yeah, exactly. That's one very good application or one very good argument. I can sort or find something in only a part of my data structure. And the the find or find if is an interesting example of that, because it might be that actually I want to find not only the first, but all the elements that fulfill that predicate. And in that case, how am I going to do that? Well, an easy way to do that is to say, well, okay, as long as as find doesn't return the end iterator, okay, that means I've found something. I'm going to do whatever I want to do with that particular element. And then I'm going to do another find, but I'm going to start from the current position plus 1. And that's easy. That's just plus plus iterator. So if I use that as the begin iterator, I can simply do repeated searches for the same thing in the same data structure without having to have a separate function for that or separate definition for that. So that is indeed a very good argument to have this sort of API in order to be more general. So indeed, that is a very valid reason why this was implemented in this particular way. There is another reason why this is actually useful as well. And containers in the STL typically have these begin and end iterators. They're defined on them. But of course, if you have your own data structures, maybe that's not so much the case. But you might have a different way to sort of indicate the first element and the last element, and how to go from one element to the other with the plus plus operator. So basically, this allows you, if you have something that represents the beginning and something that represents the end, and the prefix increment operator, the pre-increment operator is overloaded, then actually it will work without you having this begin and this end stuff. So basically that is another reason. It makes, again, these algorithm implementation just a little bit more generic, not specifically tied to STL containers, but even a bit more general. So that's actually the reason why this can be useful. And essentially, that means that I can use these algorithms just with a plain old C++ array or plain old C array if you want. I have to be a bit careful at the end, but okay, I could do that actually. Okay. What am I doing here? This is a subsequence search. So essentially, you can search for a sequence, a subsequence in a sequence. So I would have, for instance, a long string that represents DNA. So a lot of A, C, Gs, and Ts. And I'm looking for a certain substring, or in this case, a sub sequence. And that's this guy here. So that I can use the search algorithm that is going to take the begin iterator and the end iterator of the container I'm searching in. It's also going to take the begin iterator and the end iterator of whatever sequence I'm searching. And apart from that, it works pretty much identical to the find function. So if the search function doesn't return the end iterator of the sequence you're searching in, you found something, and it will actually, the iterator will actually point to the position of the first element in that sequence, in that subsequence. Okay. So that's the difference between find and search. Find single element, search sequence of elements. Okay. And then again, under the hood, intelligent things can be done. For instance, there is the Boyer-Moore algorithm in order to implement this. And that's a very good implementation. It's a very efficient implementation. So does the STL use that? I don't know, but it could. So basically the specification, of course, doesn't say so. I think it says that that would be a very good idea. So it's pretty, it's to be expected that actually it's done under the hood, but yeah, it's of course not part of the specification. Okay, and there are a number of similar things like count, count if, and so on. And I need to shift my slides a little bit because they seem to drop off the screen. That's better. Well, no, I don't want that. Okay, and that's a little better. All right. So transformation. You can transform one sequence, many sequences, well, not many, 2 sequences, and so on. Let's consider a single container. So we have, in this case, an array v1 and an array v2. An array, as you know, has a length which is specified at compile time, hence the 10. So each of those arrays has 10 elements. Note that I did initialize v1. I don't initialize v2. Okay. Now we have the transform. The transform takes at least 4 arguments. The first argument is the beginning of the container which I want to transform. The second is the end. The third element is the beginning of the container I want to the transformed elements to go into. So essentially, v1 will be unchanged. v2 will be filled with the elements of v1 after applying the fourth element, the fourth argument, and that is, of course, in this case, a function and a lambda function. Of course, it can be anything I can call. So it can be a function object, it can be a regular function, it can be a lambda function, whatever I want it to be. Okay, so again, x is the argument of my lambda function, and this means that each element of my original vector v1 will be squared, and the result is going to be stored in the corresponding element of v2. Okay. Now this presupposes that v2 is large enough. So v2 should at least be as large as v1. If that's not the case, I'll most likely get segmentation fault. At least I hope so. Things might also go boom later on, but hopefully you get segmentation fault immediately. Okay. That is also why v2.end doesn't need to be specified. Because transform is going to assume that v2 has at least as many elements as v1. That's in the assumption. So I can use this. This again is interesting because I can use this to fill a much larger container. Because I can start at the beginning and then for the next part do another transform with another vector, and then don't start at v2 begin, but where we ended up the last time. So basically, that again allows for more flexibility. Okay, what else do I need to say? Well, basically, again, you see that for v1 we use c begin and c end. We're not going to modify those. We're going to copy the elements, apply the function to it, and put that in v2. So v2 just as a begin, not a cbegin. Okay. We can also do stuff with two containers. So basically we have a v1 and v2 in this case, and they happen to have the same type of elements, but that's of course not a requirement. And then we have a third array, v3. And again, we don't initialize that because we're going to initialize it using transform. Okay. And in this case, just for the fun of it, we define two constants, w1 and w2, and they essentially represent weights. And what we will do is compute a weighted sum. So each element of v1 is going to multiply it by w1. Each element of v2 is going to be multiplied by w2. And in v3, we will have w1 times the element of v1 plus w2 times the element of v2. That's essentially the idea. So now, of course, we have 5 arguments rather than 4. Just as before, we have v1 begin, v1 end. We're not changing them, so constant begin, constant end. Then we've got v2 cbegin. So that's the first element of our second container. Again, we're not going to modify it, so cbegin. And then we have v3 begin. So basically, that is just a begin because that's the container which we're going to fill. Again, there are a few assumptions. So v2 should have at least as many elements as v1. It can have more, but at least as many as v1. Similarly, v3 must have at least as many elements as v1. It can have more, but at least. So those are the assumptions, and yeah, not abiding by them is going to give you a lot of headache. Now, of course, the transformation function itself is going to be a function with 2 arguments, and the first argument has to have the type of v1. The second argument has to have the type of v2. In this case, yeah, I know, boring, double and double, but I indicate it by colors. So the blue guy is v1. So the x argument here is going to be the element of v1. v2 is the green guy, so y is going to be the element of v2. And then we do some computation, whatever. And in this case, I capture by value for w1 and w2 to be used in this lambda function, just by way of illustration. Okay, so pretty straightforward. So this is actually quite nice because a lot of C++ comes together here. On the one hand, containers, iterators, lambda functions, and so on. So we get quite an interesting mix of C++ features. And the sum is more than, well, the total is more than the sum of the parts. So this really gives you a lot of power thanks to combining these features. Okay. There are other things like for each, replace if, and so on. So those are going to modify containers, of course, so they do something slightly different. Okay. So we already went more or less through them. There are lots of other algorithms. All of, any of, and none of are interesting. They don't only save typing, but they're also lazy, which is good. So essentially, a good implementation of all of is going to iterate over your container. And the first time it encounters an element for which the predicate is not valid, it's going to return false. So it's not going to go through your entire container if it knows it doesn't have to. Similar for any of, any of is going through your container, and it's going to stop as soon as it finds the first element for which the predicate is true. Because then any of is going to be true and all the rest need not be checked. Easy. And of course, similar for non-of and so on. So it's not only a matter of typing less code, but also a matter of people have been thinking about this. And if they thought about it, you don't have to. Again, the more you don't need to think of, the more time you have to think of the things you have to think of about the domain you're actually working in, rather than how to write code that is efficient. Question in the chat. The meaning of this, the equality thing. Okay, let me go back for a second then. And there is another question apparently. Yeah, of course. Well, basically, it depends on what you mean. So it can only be used with random access. Yeah, depends on which one. Yeah, so some algorithms, of course, will depend on the fact that containers are sequences, that you can access them by index, but at least as possible. And in the documentation of an algorithm, it will say which type of container it can deal with. So we already discussed families of containers in the sense that containers that are ordered, containers that are non-ordered, etc., sequential and non-sequential, and so on. So for each algorithm, you find which type of container it can deal with. So that depends on the algorithm. Okay, why is there int before lambda? Okay, let me go back, because the two last questions here are in fact both related to lambda functions. So let me backtrack for a second. But let's look at the, oh yeah, there is no int here, indeed. It's missing. This is going to compile because of a very old C rule that in fact if you don't specify anything, the return type is going to be int. Okay, yeah, that style. Either I forgot about it, which is possible, or I didn't put it there because, as you can see, I have very little space left on this slide. One of the two of them, I don't remember which one. I can get away with this, but it's bad style, that's for sure. Then the equality sign thing. So basically, this is the capture. So this specifies which variables I can use in the body of my function. There are a number of options. If it's empty, I cannot use W1, W2 in this function here. Then the compiler would say, okay, that's nice, but W1, W2, unknown variables. What are you talking about? I can capture them by value, and that means all the values which I use, all the variables which I use inside of this function will have values that are copied from the calling context. So basically, W1 in this function is going to be a copy, well, no, its value is going to be a copy of the value of W1, which is defined here in this line, and similar for W2. So this is captured by value, and in this case, I don't care. It's just a double precision number. Whether I copy it or not, nobody cares. That's a zero cost operation, so I don't care. If, of course, I would want to capture something that I should not copy, like a vector or something like that, then I can put an AND here. So what is this called? An ampersand here, and that would mean capture by reference. And then, of course, in this particular case, W1 would be a reference of the W1 outside of the function scope. So that's essentially the idea it's capturing. And you can be a bit more precise. You can say, okay, I only want these and these particular values to be captured by value, or by reference, or a mix of the two. So you can be very precise here. I have been a bit sloppy. I just say, okay, capture anything by value. So that's the semantics of this. There is a slide about that somewhere. I think it was chapter 4. I'm not entirely sure. But there is a whole slide about this which kind of details that. Okay, I think this might be a good time for a break because we have been going on for more than 1.5 hours, so I think you need some refreshment now. Okay, any questions at this point before the break? Not in the room, not online. Okay, then let's have a let's say 10 minutes break. And now there is a question. Let's see. Okay. Yeah, no problem. No problem. I just don't remember in which chapter it is exactly, but there is a slide. I am very sure about that. Okay, let's break for 10 minutes. As usual, I'll put that here. Always convenient. Break till we're now. Okay, let's make that 11 just to make it a round number. That's a little bit more than 10 minutes, but then again. Okay. All right. See you in a short while. Meanwhile, I'm going to do some administration, like taking attendance. Okay. No, it's 0401. And does that mean I have to include April's Fool joke here at some point? Don't tempt me. Yes, sorry, you have a question.
Because I'm not on the name list there.
Yeah. No problem. I'll pass around a sheet of paper so that you can put your name. I forgot last time, but
Yeah.
if you were there last time, then you can also write down your name.
Yeah.
I'll make two separate sections, one for this session and the session before. So, yeah, that was my plan. That is very annoying. When did I use it last? That's a very good question. Okay, maybe it's here somewhere. Because I think I lost it on Friday. And that would mean in this room, so I'll check. But I have another. So there you go. Alright, so this would be for 2025 03, and that was what was that? I need to check, don't remember. Okay, that's done. And let me quickly check my agenda because I really don't remember the date of the previous session. Let's see. That was the 26th. Yep. Okay. And that is 2025 0401. Also called today. So there you go. Meanwhile, I'm going to search for my other pen. Okay, thank you.
Thank you.
Yeah, you know, the vending machines and the coffee machine as well,
Yes.
so don't need to repeat that. Mocht je gewoon even kunsten, dan ga ik gewoon.
Ja.
Sorry, ik ben Facebook, dus ik weet wie hem.
Ja,
Dat
ja.
was. Administratie ook.
I would say, bijvoorbeeld in Fortran heb je heel vaak dat je een nuttige datastructuur met een graph enzovoort, maar die lijst is totaal niet inherent heeft. Is er een equivalent van de STL voor Fortran? Of is dat...
Niet op die manier.
Ja.
Alleszins, er zijn een aantal redelijk Fortran libraries die een aantal datastructuren implementeren, maar het voordeel van de STL is dat het allemaal heel zelfconsistent is. En dus in Fortran bestaat de kans dat een mix en match wordt van verschillende libraries en dat je eindigt met algoritmes te willen gebruiken op het een, op datastructuren op het andere, dan moet je je eigen interfacing doen en de datastructuur komt prettiger van.
Ja, inderdaad.
Dat is een nadeel. Dat wil niet zeggen dat het niet kan, dat wil niet zeggen dat het niet performant kan gebeuren, dat is weer een extra stap die tricky is.
Ja. En zou je eventueel gewoon kunnen interfacen naar Fortran naar C++, of is dat...
Nee, dat kan.
Okay.
Dat is zeker met Fortran 2018 is dat nu officieel in de Fortran specificatie.
Ja. Ja, want met C had ik al gedaan, dus met C heb ik al eens een keer gebind om een deftige solver te gebruiken en die te overkopiëren uit 1984.
Ja.
Maar ik wist niet of dat C en C++, of dat zo makkelijk
dat gaat
interchange. Ja, oké.
Nu, in principe, het zijn C-bindings.
Ja.
Dus voor sommige dingen gaat je waarschijnlijk toch nog een beetje C-local moeten schrijven om het dan deftig aan te krijgen, maar oké.
Ja.
Dus
Denk mijn
het is
leven.
een beetje twee stap dan. Hè. Dan is het eigenlijk Fortran C, C, C++ en dan zet je er.
Ja, oké.
Maar goed, dat is normaal gezien zou dat min of meer mining moeten zijn.
Oké. Dan gaan we deze een keer bekijken, want er zijn wel een aantal dingen van graphs enzovoort dat eigenlijk bij ons heel nuttig zouden zijn om dan heel mijn eigen Fortran implementatie te gaan schrijven. Die is misschien een beetje overkill.
Nee, het is dat, want ook zeker datastructuren op graphs voor te stellen. Ja, ook daar weer hangt het ervan af welke dat je best kiest, al naar gelang de algoritmes die je erop moet toepassen. En dus ook daar is het weer een subtiele kwestie van, ja, wat wil je met je datastructuur gaan doen at the end of the day?
Ja.
Ja, want een max-flow is niet noodzakelijk even gemakkelijk op een zekere representatie van een graph als een, weet ik veel, een shortest path of whatever. Dus ja, daar moet je ook weer uitkijken.
Maar het is eigenlijk eerder het aanpassen van graphs van thema en problemen. Het is heel stom misschien, maar dat is, ik doe eigenlijk grid-generatie, heel speciaal geval waardoor ik niet gewoon de classic dingen kan gebruiken, Gmail of weet ik veel wat. Maar een van de problemen is dat je eigenlijk twee lijnen hebt en daartussen moet je faces gaan vormen, maar je moet zien dat die niet overlappen enzovoort, en dat die zo elkaar kunnen zien, dus die verbindingen worden nog en dan moet je gaan kijken van oké, als ik hier één vertex verbind met een andere en ik haal die uit mijn graph, is dat dan nog altijd een volledig geconnecteerde of niet? En dus,
dat zou je niet, ja. En natuurlijk, ja, je hebt natuurlijk libraries die dat soort dingen doen. Ik denk aan de Metis, de Varmetis, en de Scotch, dat soort zaken, maar dat telt niet.
Wel, ik heb nog niet zo naar gekeken eigenlijk. Dus ik ben pas bezig met dat soort problemen echt te tackelen, want vroeger ga ik ermee weg met gewoon heel eenvoudige geometrische regels eigenlijk, die dat ik nu merk van in een aantal gevallen dat ik nu begin tegen te komen dat die niet meer houden. Dus nu pas ben ik nog tegen dat probleem aangelopen.
Dan zou ik eerder eens...
Metis of Scotch?
Metis en Scotch, ja, inderdaad. En er is een parallele versie van Metis die Parmetis noemt. De Scotch, waarin je, en nu offend, ik denk dat je die ook kunt programmeren met support voor NPR. Compileren met support voor NPR. Dus, en dat is industrial strength bij wijze van spreken. Dat zijn libraries die gebruikt worden in de grote pakketten.
Oké, nou moet ik dat zeker bekijken.
Ja. All right, let's continue. Let me continue by sharing my screen. And let me also get back to the slides. So other algorithms. As I mentioned, it's always useful to use them, even if they seem trivial to implement because people have thought about them, use certain optimization tricks, and again, the least you have to think about details, the more you can think about your domain-specific problems. So there's also things like mismatch. Find the first position where you have a mismatch between sequences. So that's sort of the opposite of search, if you want. Equal. So this is also quite useful one, because just asking whether V1 is equal to V2, yeah, that's not going to be an element-wise comparison. That's just going to see whether the objects V1 and V2 are the same object. So that's, yeah, sort of equality, but it's object equality. So if you want a true comparison at the level of elements, you should use equal. And then, of course, you can guess that there is an optional argument, which is a predicate that defines equality in the context which you have. Okay, copy, move. So copy and moving a sequence to another sequence. So copying is pretty obvious. Moving means I get the values of one sequence out of it and into another one. So this is an interesting one, and we'll come back to copy and move semantics. Maybe today, but it's not such a simple subject, so we'll see. Removing elements from a data structure is not trivial, typically, so it's always good to use an algorithm for that as well. Shuffle, etc., accumulate, and inner product. So these are, of course, interesting ones, because accumulate, for instance, will allow you to do the sum of elements, the product of elements, whatever you can define as an accumulation. And then, of course, by default, it's going to be a sum, or whatever the plus operator defines. But for you can also define your own function that encodes the reduction. At the end of the day, an accumulation is a reduction. So you can define your reduction function, and you specify the initial value, and that means you can create a sum. You can create a product operation out of that, depending on what you need, and more general things if you want to. Then in a product does indeed what you think it does. Give it two vectors of equal length, and it will produce a scalar, which is the inner product of the two vectors. So basically, if that smells like this inner product, if that smells like linear algebra, at this point in time, there is not much support, if any, for linear algebra in C++. But in C++ 26, support will be coming for linear algebra. So that will be very interesting for scientific computing. But yeah, before we're able to use that, it's likely to be something like 2028, 2029, something like that. Before the compilers support it, do it efficiently, and so on. So it's on the horizon, but at this point in time, it's still even beyond the horizon. Even in the specification, its specification isn't published yet. But if you like, you can read about it. It's already, the draft is already available, so it's obviously subject to change until it gets ratified and becomes the official specification. We will talk a little bit about linear algebra later on, but first, let's turn to ranges, because ranges are in fact quite useful and again related in a way to containers. So ranges allow you to define views over containers, I'd say. I think that is the best way to put it. And okay, why bother? Well, basically because they help you compose algorithms. Because if you look at the implementation of algorithms as we've seen them up to this point, they all take iterators as arguments. Begin iterator, end iterator, blah, blah, blah. Okay, but that means that suppose I have a transform operation that takes an array, transforms it into an array, and then I'd like to do a sort on that. It means that I first create a new array with the transformed elements, and then do the sort operation on that. Okay? This is a bit of a, no, this is not the best example actually. But basically, it would be nicer if I wouldn't have to create intermediate stuff. In this case, it doesn't matter. So let me try and find a better example. Suppose you have a transform, okay? And that the result of that transform, so that's a new array, is going to be used in another transform that takes two sequences. Okay, so that means I first need to create a new array for the first transformation, and only this I can use as input into the second transform for the two sequence transformation, for instance. So that means there is an array which I'm likely to just throw away later on. I just needed to store the transformation result of the first array because I need that as input to the second one. So yeah, that's a bit of a thing. And basically that's where ranges come in. So let's consider this example here. We have data, and data is somehow something of length 20, whatever it is. And it's some abstract thing, it's a container, it will obey all the rules of containers, it will have a begin, an end, and so on. So whatever it is, it's just something abstract which I define myself. Okay, so now I can do a copy if. Okay, so that means, what am I doing? I have a second data structure, T1. Okay, and that data structure must have a property. It must have a pushback. I must be able to either push or push back. So I must be able to append something to it. Okay, so I'm going to copy all the elements of data into T1, but only if the numbers are even. So that means data somehow holds integers. Okay, and in order to fill the T1, I'm going to use a back inserter. So suppose that data would be a vector, then this back inserter for T1 is going to be a pushback. If it were a stack, then it would be push. Whatever, the compiler is going to figure it out, and there are definitions for when to use which particular function in order to put something at the end of a sequence, of a container, whatever that container is. Okay, so this is only going to work if such an operation exists. If such an operation does not exist, fine, then the compiler will tell you, okay, you can't do this. There is nothing, there is no back inserter for this particular data type. Okay. Then I have a second data set T2, and this I'm actually going to define as with a copy constructor. So I'm going to copy it from the T1, but I'm going to skip the first few elements. So skip is just an integer, for instance 3, and that means the first element I'm going to put into T2 is in fact going to be the fourth element of T1. So something I didn't tell you about iterators, but which I kind of implied, I can do integer arithmetic, well, addition and subtraction with iterators, in the sense that if I add an integer to an iterator, that actually means move that many positions ahead. I can do the same thing by subtraction. I can say, okay, move a number of positions back. So essentially, T1 end minus 1 would give me the iterator which points to the last element of T1. Okay. T1 begin plus 5 would point to the sixth element, I think. I think it's the sixth element of T1. Okay. So that works as well. So that's what I'm using here. In this particular case, I just don't want the first skip elements, whatever skip is, some integer value. Okay. So T2 is going to be populated by elements of T1, but it's not going to be the same size. And then I'm going to iterate over T2, and I'm just going to write the elements. So if you look at the, let's suppose that this is more or less complete code. So I'm not using T1 at the end of the day. I'm only using it as an intermediate in order to create T2. So I would prefer not to have to do that. And in a way, there is no reason to do that. Because if you look at what is happening here, then I'm filtering the elements of data, and I'm going to skip the first skip. If I get them, I'm going to ignore them. And then I'm going to fill T2 with the remaining elements that are even. That's the semantics of what is here. Of course, the intermediate step of creating T1 is in fact just overhead. If I look at my code, there is no reason to do that except the technical reason that otherwise I can't skip these first few elements. Okay. So this is of course a drawback. If you like, you can also think of that in terms of matrix operations, for instance. Because consider a matrix expression, 3 times A plus 5 times B, something like that. Okay. Now, you can do several things. You can create a new matrix, temporary matrix, that contains 3 times all the elements of A. Then you can create a second temporary matrix that has all the elements of B multiplied by 5. And then you get your final matrix, which is just the sum of these 2 intermediate matrices. But if you do it that way, you created 2 potentially large matrices, which you had to fill with elements, and then get the elements again, add them, and so on, and that's a lot of overhead. So that's something that you hope doesn't happen. Okay. Now, of course, if you look at this semantically, the only thing you need to do is an element-wise operation. Your resulting matrix, each element is going to be 3 times the element of the first matrix, corresponding element, plus 5 times the corresponding element of the second matrix. And you can do that element by element without ever creating an intermediate matrix, let alone 2. So it's a bit similar thing there. So if you have something that can avoid that, like for instance, a Fortran compiler will do for you, then of course, that saves you a lot of, on the one hand, memory, because you don't have this construction of intermediate matrices that just take up memory space, but of course also a lot of performance, because filling these matrices is going to take quite some time due to memory bandwidth and so on. So basically, that is to be avoided if possible. So that same reasoning applies here. You also have intermediate results, which are just an artifact of the fact that you want to use these algorithms. Okay. So that's cool. That's something to be aware of. Is there also a way to get around that? Yes, is the answer. The answer is use ranges. So what you already saw when we went through the documentation of the algorithms part of the STL, you saw that for each algorithm, there was a ranges counterpart. Here it is. So basically, this is using ranges. And ranges define, as I already said, they refine views. Now, why is it reverse here? Yeah, okay. I missed the R here. I just didn't see it. I thought it was a C, but it's actually an R. So, okay, let's backtrack a little bit and let's pay attention to details rather than assuming that they're not there. So this is an R begin and an R end. Okay? So this is a reverse iterator. So the R begin actually points to the last element of my container, and R end points to an element just before the container begins. So it's the reverse situation of begin and end. R begin is the last element, begin is the first element. R end is just before the container starts, before the first element. End is just after the last element. So it's just the same, but reversed. So that means that if I execute this for loop, and yes, there could be a reference here, that means we start with the last element of T2, then the one before last, etc., until the first element of T2. So that's the R begin, R end. Sorry, I just missed it when I was looking at the slide. Okay, so what we can do is use views instead. And essentially, you create views, and such a view expression you need to read from the inside to the outside to interpret it correctly, the order in which things happen. So the first thing I'm going to do is to create a filter view, and I'm going to create a filter view on data, and my predicate is even. Okay. So basically, this doesn't create anything in a sense. Yeah, it creates something, it creates a view, but it's not going to necessarily copy elements. It's not necessarily going to create an intermediate copy of that data structure. It may do that if it has to, but a good implementation will avoid it if it can be avoided. Okay. And then the second operation is a drop view. So that is essentially saying, well, okay, drop from this view the first number of elements. In this case, skip elements are going to be dropped from that view. Okay. And then the last step is a reverse view. And yeah, that is fairly trivial. That's just going to give you a view on that data such that the last element is the first one you get, and the first element is the last one you get. Okay. So semantically, this thing and the code above do the exact same thing. So RV is going to be all values in data that are even, except for the first skip, in reverse order. So those two code fragments do the same, have the same semantics, same thing seems to be happening, but the second one is not going to create intermediate copies. And that, of course, is a pretty interesting performance boost. So some views, of course, well, all views will create intermediate data structures, but they should be lightweight with respect to creating the full-blown thing. That's the idea. Okay. All right. I would also argue that this code is more elegant. But okay. So what is annoying and what makes it a bit more elegant but not extremely elegant is that you actually need to read the code from the inside out. And also, if you're building your expression, you should start with what you want to do last. And then the operation which you want to do just before that. And then at the end of the day, the first operation you want to do. So that it's a bit unnatural. But of course, that's the nature of composing functions. So yeah, that's how things work. Except that there is actually, but that is C++23, that there is actually the pipe operator. And that is familiar to people who use R. Unfortunately, Python doesn't have it, which is a major source of frustration for me. Julia has it. So there are a number of programming languages that have this pipe operator. And for ranges, it's also defined in C++. And for me, this is really a big win. Why? Because now I can, in fact, simply pipe data into a view algorithm. So this I can read from left to right, and it will be in order of execution. So basically, I'm going to feed data into the filter view. Okay? And yeah, okay, that's correct. And basically, now it takes a single argument, only the predicate, because the input is going to come from the pipe operator, so that's going to be data. So data piped into filter with the predicate is even is going to create a view of all even elements in my data container. Okay? The output of the filter operation is the input for the drop operation. So of these even number, the first skip are going to be dropped. They will not part of the resulting view, and the output of that drop is going to be the input for the reverse view. Okay, that is our final view. So if you look at this whole expression up to this point, this is actually our final view. First filter, well, feed data into a filter, feed the result of the filter into a drop, feed the result of the drop into reverse. So we've got our view, just like in the code above, code fragment above. So the whole thing, from data up to, so from here up to down below here, that is going to be the view I'm going to iterate over. So value, the first value is going to be the last even number in data. The second is going to be the one before last, etc., until we've exhausted that particular view. Okay. And personally, I would consider this quite elegant. I'm really a big fan of the pipe operator, if it exists. And fortunately, for ranges in C++, it does. Okay. So it might seem a little bit magic, might also seem a little bit counterintuitive. If you've never really worked that much with a programming language that has this feature, then this might seem a little bit like magic. However, you are very likely to have worked with it, in the sense that if you have written a bash script, then you have used this pipe operator most likely quite a lot. In the sense that, for instance, find something, pipe the input into grep, etc., etc. I mean, that kind of thing is something that on the shell you do very regularly. It's the same semantics here. So there is nothing magic. It's just like the shell pipe, which you are most likely familiar with. Okay, there is a question, I think. So let's see. What will happen if I use rbegin or reverse view? Yeah, so basically, there are some data structures that do not support reverse views or the rbegin and rend. So in that case, the compiler is going to tell you that you can't do that on that data type. Easy. You might get a horrible template error, which takes you like 5 minutes to figure out what it means, but the compiler will tell you that you can't do that. That is, by the way, one of the, I didn't mention it yet, I think, but one of the drawbacks of using templates, also of the STL, the error messages you get can be somewhat intimidating in the sense that there are 5, 6, 7 pages with a lot of internal stuff that you don't have a clue about what it means. So if you're in that situation, go to the beginning of the error message. That's where the information is going to be. All the rest is gibberish. No, not gibberish. That would not be the right term. But is about stuff you don't have control over because it's something template internal, which has been constructed for you, and which basically you don't have a clue about what it looks like. So basically, that is a drawback of using templates in general, and of using the STL specifically. Work is being done to improve this. Lots of work is being done to improve this, to be specific concepts. We'll talk a little bit about concepts later. But that is going to be bloody annoying. Okay. So basically, a reverse on a reversible container should be very cheap. It's just iterating over the other direction. So essentially, it's going to be a bit more expensive than a forward iterate, because most likely, well, okay, not most likely, but it could happen that the compiler is not going to generate prefetch instructions. If it's smart, it's going to do that, but maybe it's not smart enough to figure that out. So yeah, you might lose a bit of performance when iterating backward over something than forward over something. But that only applies when you have contiguous storage. If you have a data type that doesn't store its data contiguously, then yeah, it doesn't matter anyway. Okay. So this is, of course, this remark about being more elegant is, of course, very subjective. I like pipes. For me, it's nice. That it's compact is true. I mean, if you look at 2 code fragments, it's pretty clear that the second one is, in a way, more compact than the other. But okay, your mileage may vary, so that's a matter of taste. Okay. So this will result, well, okay, not particularly the piping thing, but using ranges in general, and that's what's meant here, can in fact give you a performance boost due to the fact that you don't need intermediate data structures in many cases, and so they're not going to be generated in the first place by good implementation of this ranges thing. Many of those are implemented in C++ 20 compliant compiler distributions. Quite a lot of the C++ 23 additions have already been implemented, but not everything. So that's a little annoying, but yeah, that's how things go. Okay. So in a way, I would argue that if you use modern C++, it doesn't differ that much from Python, even in the length of the code. The only thing you need to add is, of course, types. Type declarations you need to add. But apart from that, the core functionality is expressed very compactly. So basically, if you look at this particular code, so here we use the enumerate view. For the Python people, does that remind you of the enumerate function? So well done, because this does the same thing, essentially, in a somewhat different way, but you can guess what's going to happen. So if I create an enumerate view over my data, what I will get as iteration values are tuples. The first tuple the first tuple element is the ID, so 0, 1, 2, etc. For the enumeration of the elements, and the second is a corresponding value. And I'm using a C++17 feature here, basically automatic tuple assignment. So what the view is going to return is in fact a tuple, but I can unpack that into as many variables as, of course, the tuple has elements. And it will have two elements here, an ID and the value. And I can simply do const auto, and that is going to be an integer, and this is going to be the type, whatever is in my data structure. And then I can just use these variables as I would in any other loop. So if this looks quite a lot like Python, yes, it does. In fact, this code would be just as long, and it would do the exact same thing in a way. You would call the enumerate function on your data structure. You would use that in a for something in the result of enumerate, and you would do something in your loop. The exact same thing. A bit more verbose, but still the same thing. Okay. So I didn't talk about stream iterators. I didn't discuss iterator types, but we touched upon them already. Reverse iterator and so on, where you can use what constant iterators. So we touched on that. It's a bit broader than that. So basically, I prefer to have some more examples on the one hand, and also I wanted to talk about ranges and views, which at least was not in the edition of a Tour of C++ I had. I really don't know whether it's in the latest edition. I hesitate a little bit to buy the book a second time, so I don't know what's in the latest edition. But it might be that it's added meanwhile. Okay, any questions about this? This is nice C++.
So more complex.
Well, so the remark is, yeah, it's nice C++, yes, but on the other hand, it's more complex. I don't know. If you come from this with a Python background, I think you'd actually like this, because it's very similar. Yeah, there are indeed a few concepts which you need to be aware of, but the tuple unpacking thing, so this unboxing here, yeah, that's something that you do in Python as well. So a Python programmer would recognize this. Okay, as soon as that Python program is able to read through the gibberish of const auto, blah, 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 that kind of thing. But apart from that, conceptually, it's the exact same thing. So I don't know where it's more complex. It looks weird, but that's just a little bit of getting used to, and then basically it's Python. But okay, that's my opinion. All right, so yeah, basically there are a lot of algorithms, and personally I find this a good book. It's a very old one, because this is the umpteenth edition. I think by now it's up to the 4th edition, meanwhile. But at the end of the day, nothing much changes with algorithms. Well, a few new ones probably, but the old ones are still very valuable. So if you want a reference book on algorithms, then I can definitely recommend this one. Okay. Let me see. We definitely need to talk about copy and move semantics, but that's a slightly challenging subject, and I hesitate a little bit to do that now. Let's perhaps not, and keep that for tomorrow morning when we're fresh, because that will require some concentration to get that digested. And indeed, let's talk a little bit about numerics, because yeah, I mean, that's usually what we do in scientific programming, so let's do that. Okay, so one of the things we didn't discuss yet is complex numbers. We've talked about real numbers at length, float, double, single precision versus double precision, but we also have complex numbers. Well, have them, yes, sort of. They're part of the STL. So C++ itself, as a language, has no clue what a complex number is. So again, it's implemented using templates and hence part of the STL. Okay, you include complex, and then you can start working with complex numbers. So complex is a parameterized type, it's a generic type, and what you specify is the type in which the imaginary part and the real part are stored. So complex double obviously means real part and imaginary part are stored as double precision numbers. So obviously I can have complex float, and then I'd have a single precision real and imaginary part. Nothing special going on here. Okay, so I can simply create a constant value, complex value, by specifying the real part and the imaginary part. Quite easy. And this would be a constant, of course. Okay, I'm iterating over x and over y. Nothing out of the ordinary here. So I'm going over x in steps of 1 per 1000 and over y in steps of 1 per 1000. Okay. And then for each x and y, I'm going to create a complex number with x as the real part and y as the imaginary part. It would have made sense to name my variables a bit more sensible, like im and re and im or something like that, but okay, whatever. It's pretty clear what it does. Then I check the norm of set, so the complex norm of set. If it's less than 2 and m++ less than max, etc., then I perform this complex arithmetic operation. So I multiply complex number z by itself, add complex number c, and so on. So basically that means the arithmetic operators, addition, subtraction, multiplication, division, have all been overloaded, been defined to work properly with complex numbers. Many of the, where it makes sense, of course, many of the mathematical functions have also been overloaded to operate on complex numbers. So it's quite transparent. Okay. And then, at the end of the day, we print something never mind. So basically, that's how you can use complex numbers in C++. So again, it's fairly straightforward. So what you don't have is this notation like you have in Python with a J that denotes the imaginary part, of with the suffix in, which you would have in Julia, for instance. So here it's just, at the end of the day, a struct with a or a tuple. I don't know how they implement it under the hood, but essentially just two double values, and all the semantics is in the overloaded operators and functions. Okay, and if you execute that, you get a pretty plot, which you will recognize as something Julia set-like. So basically, that's what this does. Okay, so if you want the real part and the imaginary part, you can call the real and the imag function on a complex number. So that's also useful to know, of course. And in general, but that is just, has nothing to do with C++ as such. But of course, computing the norm and comparing that to some number is of course a fairly expensive operation because there is a square root involved. So that is expensive. So basically, rather than comparing square root of something to something, it's easier to compare the something to the something squared. And that's exactly the remark here. So basically, rather than comparing an absolute value of z to 2, you just compute the square of the absolute value and then compare that to 4. And yes, it improves performance pretty significantly. So yeah, that's just something I want to mention. Something that's also quite useful is the limits header. And that for integers, for instance, that is going to define a number of interesting things, like for instance, the smallest integer. And you get that by using std numeric limits. Then you specify the type of the integer you want and the minimum function. So this is templated, so it will give a different result for each integer type. Well, it will give the appropriate result for each of the types. And the same thing with max. Okay, so for floating point, of course, you can do a bit more. You can also ask for the minimum and the maximum, but you can also ask for epsilon. And epsilon is an interesting value because that is the smallest floating point number, so that if you add it to 1, the result is going to be different from 1. There is such a number because, of course, the set of floating point numbers, whether they're single precision or double precision, is a discrete set. So basically, it's a finite set. So essentially, there are gaps between your real quote-unquote numbers, and so epsilon is essentially the gap between 1 and its successor. So this is quite useful in certain operations where you need to know the numerical precision of your. It is a good gauge for the numerical precision of your operations. And of course, again, it's templated, so this would give me the value for double precision representation. If I use the float type here, I'd get it for single precision. Okay. You can also get the significant digits in base 10. Of course, that only works for floats, so basically things like that you can easily get. There is some other interesting stuff in there, basically to test for, let's say, special numbers. Because you may or may not be aware that the IEEE standard for floating point values actually defines values for a number of things. Like positive infinity and negative infinity. So these values exist. If you compute with them, you get more infinities, but okay, they are represented. There is also a value none, which means not a number. And for instance, if you have a floating point number, which is negative, strictly negative, you take square root, the result is going to be a value. That value is going to be none. So it's not an error as such. You can still keep on computing, but of course you will get more and more nonce, because basically anything you do with a none is going to result in a none. Not a number remains not a number, whatever you do to it. So that allows you, these functions allow you to check whether something is finite, whether something is none, and so on. So a number of these values, so for instance, for int 8, minimum would be minus 128, maximum would be 127, int 16, and so on. So basically, these are your typical values. One of the things which I already mentioned, but maybe let me repeat it. So how many bits int, short, int, and long are in fact not specified either by the C standard nor by the C++ standard. The only thing the standard says is, okay, the number of bits of short is less than or equal to the number of bits of int, which is less than or equal to the number of bits of long. That's all the standard says. In practice, usually this is the case. So short would be 2 bytes, int would be 4 bytes, and long would be 8 bytes. But you cannot rely on that because the standard doesn't say anything. So anyone who makes a CPU or a compiler is free to do different things. Okay, so for floating point values, we've got float, double, and long double. I didn't mention long double up to this point. I'll tell you why in just a second. And then you see the minimum values. So minimum in this case means the smallest positive number, strictly positive number that you can represent. So it's not the most negative number. It's the, so that's a bit different between integers and floating point numbers, hence it's worth pointing that out explicitly. The epsilon value and the maximum. So you also see the significant digits. So for float it's 6, for double it is 15, and for long double it is 18. So you get a bit more precision with long double. Okay, then why don't we use long double? Well, basically because there is limited hardware support for it. So if you switch to long double, from double to long double, your performance is going down. Is it going to really help to add 2 digits of precision? If you're in a situation where a double precision number isn't precise enough to represent your data, then maybe you're not using the right algorithm. And you should rethink the numerical algorithms which you're actually using. There are exceptions, let's be very clear. If you're into statistics and you have marginal distributions, blah, 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 yes, you need them. That's a different thing. But in general, for most scientific computations, if you can't get it done with 15 significant digits, maybe you should try another approach, because then numerically you will be in very unstable territory, and most likely this is going to blow up in your face at some point anyway. Just adding the 3 digits is likely only going to save your bacon temporarily. So that's a stopgap rather than a remedy, and it will kill your performance. So yeah, just don't do it. Long double with this definition is just a leftover of the bad old days when we had the mathematical coprocessors in your PCs. Likely none of you is old enough to remember that. But yeah, we had mathematical coprocessors in our PCs. It was a cartridge you plugged in, and all of a sudden your numerical computations went X times as fast. I don't quite remember. But those had actual hardware support for this long double, and that's where it came from. And of course, it stayed there, but now it's emulated, so it's, yeah, not nice. We don't want it. Okay, so again, the same remark holds for the double precision types. The only thing the specification says is that float is less than or equal than double in number of bits, and the same for one number. Again, no guarantees in the specification. Wait, is that true? No, that's not true. Well, I'm sorry, forget that remark. Rewind. Float is always 4 bytes. Double is always 8 bytes. Sorry, I'm getting carried away here. So that is definitely the case. Okay. Sometimes you really need more precision. There is no way around it. In that case, there are a number of options, but it is going to cost you in terms of performance. Because what you're going to do is to essentially emulate arithmetic operations, and yeah, without direct hardware support for it, that is really going to be a pretty slow thing. It's also going to additionally add to the burden of development, because using these libraries, it's not a drop-in. So basically you have to call a function to add 2 numbers together. Okay? You can imagine how nice your code is going to look. So again, if you're in that situation, try and find different algorithms, because that's going to be definitely better. But yeah, if there are situations, then you can actually do that. So if you need arbitrary large integers, just use GMP. That will do the trick. That allows you to use integers of any size. For floating point numbers, there's MPFR. The MP is always multi-precision. So basically that allows you to define real numbers with, okay, floating point numbers with, I don't know, 16, okay, let's say 30 significant digits, no problem. But you will pay for it. And for complex, it's MPC. Okay. Another thing which, and by the way, these are C libraries. So as far as I know, there is no C++ friendly API for that, which also blows up your code in terms of size and perceived complexity. So yeah, it's really stopgap. If you don't need it, don't use it. Okay, another thing which you, in scientific computing, need to do a lot, or not, depends on your field, is generating random numbers. And of course, random numbers are typically not random, in the sense that they are pseudo-random. And that's of course a good thing. Because if you have true random numbers, then how are you going to reproduce things? If you have true random numbers and you're hunting for a bug, good luck. Because now you see it, now you don't. If you can't get the same sequence of pseudo-random numbers each time, those two things are going to be impossible in case of reproducibility, because yeah, if you just get a random sequence, how am I going to reproduce things? I can't. If I get a random sequence, how am I going to debug things? Okay, I probably can, but I'm going to spend a lot of time on it, because I need to run it. Now I don't see the bug, need to run it again. Now I see it. Okay, what might be the pattern, etc., etc. So basically, having pseudo-random numbers is in fact a blessing in disguise. So how does it work? Typically, you have a sequence of random numbers, and the thing that generates that sequence is typically called an engine. Sometimes a generator, it depends a little bit on terminology. So the engine and this you can seed. So in other words, you can give it initial conditions, and the same engine with the same seed is guaranteed to give you the same sequence of random numbers time and time again. Okay. So is this important? Yes. It's also, for instance, important in machine learning, because if I start training my deep neural network, there is a lot of random number generation involved. Initializing my model, choosing which connections to prune, etc., with a what is it, dropout layer and so on. So basically, there is a lot of random stuff going on. So that means if I don't seed my random number generator, how can anyone redo my experiment? Because the outcome will be different due to the complexity, due to the order of operations and so on. You're sure to end up with two different neural networks, just depending on where your random number sequence starts. So if I don't record my seed, how can I reproduce my stuff? If I can't reproduce my stuff, what am I doing? Not science. Period. I might be doing engineering, which is cool, but not science. Okay, so seeding a random number generator is important. Realizing that you're dealing with a pseudo-random number sequence is also important. Okay, so the standard template library has its own header file for dealing with random stuff, and not surprisingly, the name of the header is just random, and it defines quite a number of things. So one of the things it defines is, as I said, engines, and there are quite a few of those. So there is STD, random device, and that is the exception to what I just said. This is one which you cannot seed, and that is something that is going to give you a sequence of random numbers for whatever random is. How does it work? Basically, it will somewhere in memory take a sequence of bits, and that's going to be converted into your value. Okay. You can already guess that the quality of these random numbers will be quite poor. Okay, what do I mean by the quality? So if you're into random numbers, you know this, but for those of you for which this is not core business, so basically, do you have a question? No. For those of you for whom this is not core business and maybe you're not familiar with it, so what do I mean by quality here? Well, what you usually want is that your random numbers follow some distribution. For instance, trivial example, you generate numbers between 0 and 1, and you want those numbers to follow a uniform distribution. So if I have a good quality random number generator, and I use that distribution to generate numbers, then I would expect that indeed, if I generate enough numbers, it will, within certain deviations, depending on the number of random numbers, it will actually follow that distribution. Okay. If I have a poor quality random number generator, that might not be the case. For instance, it could be that that random device systematically samples random numbers where certain bit sequences don't occur. Yeah, that would distort my distribution. And it's entirely possible because I don't know what's happening with random device. So it's very likely that if I were to check the resulting distribution, that would actually not be really uniform. Maybe it wouldn't, maybe it wouldn't, I don't know. But I certainly don't have any guarantees. So good random number generators give these guarantees. They will say, well, okay, within these statistical parameters, if you generate that many random numbers, then we guarantee that with this distribution, this is going to be your deviation from it, your maximum deviation from it, and so on. Okay, so that's one quality thing. And then another quality thing, which is also important for simulations, the By definition, the number of random values which you can generate is finite. Because if you generate numbers between 0 and 1, how many are there? Well, as many as I have floating point values between 0 and 1. That's a finite number, sorry. Okay, that means that if I start a certain sequence, that sequence is going to repeat at some point. Because the state of my random number generator is also finite, so at some point it will be repeating. So the correlation length, so essentially when does it start repeating, what's the distance between the repetitions? So the correlation length should be preferably as large as possible, so that there is the least correlation between subsequent values, and you have a large range of your sequence which you are sure of is not going to be a repetition. So that is important as well, and those are characteristics of random number generators that you will find maybe in the documentation or in the papers which have been published at the time when they were introduced into the literature. So that's why there is a whole family of these random number generators, of these random number engines. Of course, as usual, the higher the quality of your random number generator engine, the more expensive it is going to be to generate your random numbers. So if you don't need that high a quality of a random number generator, don't use it. It's going to hurt your performance. And don't underestimate it. Generating random numbers is a very expensive process with certain generators. For instance, this MT19937 is not a spaceship out of Star Trek, but rather a specific algorithm. It stands for Mersenne twistor and then some specification. So basically, that is a fairly expensive algorithm. It's also a very good one. But do I need it? If I'm writing a game, no, I'm not going to need it. Okay, we're not going to write games, I agree. But if, let's say, you are not really that much concerned with your correlation length, or your distribution may deviate a little bit, it might be too expensive. And it may slow you down if generating random numbers is core to your algorithm. As I said, there's a whole variety. So for instance, Ramlux 48 is quite good. Not as good as the Mersenne twistor, but it's faster than the Mersenne twistor. So basically, again, it's choosing your algorithm appropriately to the task you're trying to solve. Balance between quality and performance. Performance you will need, quality you may need. Okay, well, performance you may also not need if you generate in your whole application 5 random numbers. No one cares about which random number generator you're going to use, neither with respect to quality nor with respect to performance. So then you really don't care. But okay, that's a different thing. Okay, so on the one hand, engines to generate sequences of random numbers, and then distributions to draw them from. And there are, of course, quite a lot. So we have uniform distributions, integer and real. We have a normal distribution, we have a gamma distribution, we have a Poisson distribution, blah, blah, blah. All the usual stuff that you expect in a library for random numbers, library for distributions, you will find there. Obviously, it's not a substitute for R. R will probably have a gazillion more, but for, let's say, casual statistics users, let's put it that way. Now, the statistics people are really getting annoyed, but for casual use of statistics, it will be good enough. Okay, sometimes annoying statistics people can be immune. Anyway, so basically, you characterize your distribution by a number of things, by the type of value you want to get, because don't get confused. Uniform int distribution doesn't necessarily give you an int type. You can specify that type. So if you want for instance, a uint 8, okay, you just do uniform int distribution, and you use as a template parameter, you just use uint 8. And of course, similar for our uniform real distribution, I could use float, I could use double, no problem. And then the parameters, of course, are a and b, and a is the minimum value, b is the maximum value. For integer distributions, the a and b are both included. Or not? Wait. I always have to check this. I really can't remember it. And in a way, I don't even want to remember it, because if I try to remember it, I will probably get confused. And if I get confused, I make mistakes. So in this case, I don't want to remember it, I want to look it up. So I always look it up, because the problem is, for instance, in Python, you have some random number functions that include the last element, some that don't. So basically, you have int range, you have the other one. So yeah, I always check. So if you want to know, of course, this guy here is your friend again, cpp-ref, and we can have a look. Just going to go back here, and then where is it going to be? Good question. Numerics library sounds reasonable, and pseudo-random number generators sounds really, really promising. Okay. So this is not interesting. Here we get some random number generators. You recognize the MT19937, which I always have to look up because I always forget the bloody name of the thing. Okay, for instance, uniform int. Let's have a look. The closed interval AB. So for the integers, the B is included. So if I want to throw dice, I would use uniform int distribution for, okay, whatever type, uint 8 for instance, and I would generate from 1 to 6 inclusive. Okay, so that's for the uniform int. So let's check the real. And that is the half open interval. So A is included, B is not. Okay, so that's a choice. Does it matter? Well, not really, because essentially testing equality on floating point numbers doesn't make sense. So does this matter? No. Whether B is included or not, I shouldn't test on equality anyway. So it doesn't matter. Okay. Oh, that was the wrong one. That's better. Okay. And you've seen there were quite, well, let me maybe go back. There are quite a number of other distributions. So, oh, sorry, I have to go one back. So you have the binomial distribution, Bernoulli distribution, etc., geometric distribution, Poisson distribution, exponential, gamma, etc., etc. So, and you also have some sample distributions, sampling distributions, so you can get a discrete sample. Well, you can sample a discrete set for values, so that can also be useful. Okay, so that's the second part of the random number library, the pseudo-random number library, if you want, the distributions. Okay, so typical workflow. If you really want a random sequence, first create a random device. That will give you a true random number, and use that to generate a seed. Okay, So you need a seed distribution. You get the seed from the random device, and then you stop using it. So this gives you true randomness, in the sense that the sequence will be seeded with something that is really, really random. Okay, so if you want reproducibility, write the seed to a file, or it's gone. Okay, then create an engine using that seed. Create your actual distribution which you're interested in, and then draw many numbers from the distribution using the engine. What I see many people do, and that is really an extremely bad idea, that is creating an engine for each random number which they want to get from the distribution. I see that quite a lot. That's of course methodologically completely and totally wrong. And on top of that, your performance of your random results, because your scientific results are going to be random at that point as well, literally, it will also be even more expensive. So yeah, methodologically that would not make any sense at all. So you create your engine with a seed, you create your distribution, and you repeatedly use the engine in order to get subsequent random numbers. You get a sequence of pseudo-random numbers. Okay. So that's important to realize. So this would be the whole code for that. So the first thing is indeed create a random device. Second is create the definition of your seed. In this case, remember numeric limits. So I'm going to use the maximum value of size t. Okay, what size t? That's the type that's used throughout the standard template library to hold counts of something. For instance, if you ask for the number of elements in a vector with the size method, it's going to return a size t value. So this is, under the hood, an unsigned long value, so an unsigned uint64, so values between 0 and 2 to the power 64 minus 1. Okay, so my seed is going to be between 0 and 2 to the power 2 to the power 64 minus 1. Okay, and I'm going to use that as the seed for my distribution. So from the seed distribution, I'm going to call that with the engine, and that's going to give me the first random value generated from that distribution with this particular engine. Okay. I'm going to record the seed, because otherwise I can't redo my computation. So I'll write that somewhere so that I have a record. Then I create the actual random number generator, the actual engine that I want to use. In this case, the Mersenne twister with 64-bit seeds. That's what the 64 suffix here is doing. And I supply the seed in order to initiate the sequence, to seed the random number generator. Okay, then I define my distribution. The bind thing here essentially ensures that I get a function. So distribution is calling a function that doesn't take any arguments. So normally, distribution is a function object that takes a single element, which is the engine, like I do it here. But that's a little annoying in the sense that, suppose that I create my random engine, and my random number generator engine, and I generate my distribution, and I want to pass the whole thing to a function in order to generate random numbers in that function. Okay, so then the annoying thing is that I need to pass two things. I need to pass, on the one hand, my distribution, and on the other hand, I would need to pass my engine, which is a bit inconvenient. So in that respect, it would be nicer if I could create a function object that doesn't take any arguments, but that has the engine bound to it. And that's exactly what std bind does. Okay, so it's going to take a function, in this case, normal distribution double between 0 and 1. So this is just a uniform distribution of floating point numbers in double precision between 0 and 1. Okay, this guy is returning a function, most likely a function object. Don't know how it's implemented in the standard template library, but it's something that I can call. And then I'm going to bind engine as an argument to that function. So basically that means that distribution is now a function with 0 arguments. So if I want to pass that into a function, the only thing I need to pass is the distribution. The engine is going to be carried along with it in a way. It's kind of internalized into my distribution. Yeah.
Is that something you would rather do in an object-oriented way, having your own type definition where you have an engine that you initialize and then a function, which is then that auto distributed?
Yes, you can do that in several ways. You can create a function object of yourself. So basically, I could create a class. That class would have a constructor. That constructor would take an engine reference as its argument. It would store that engine reference in a private attribute, and it would overload the round bracket operator, and that would call the distribution, which is then, is the second argument. We'll have 2 arguments. And the distribution will be called using the engine, which is an attribute of your object. Yeah, that would be one way to do it. That's the classic object-oriented way. You create a class with an overloaded call operator. You can do that in Python, you can do that in C++. So that is one way to do it, exactly. And that will work perfectly fine. Only it takes code and it's an extra class. So there are alternatives. One alternative is this one, bind. So that sort of does the same thing. What it actually does in computer science technical terms, it's going to carry the function. So it's going to fix, in this case, one of its arguments, but you can use bind to fix multiple arguments in a function if you want to. In this particular very compact form, it's just going to have a function with one argument, binding that one argument to the function parameter. So the net effect is that I now have a function with 0 arguments, and it's shorter than having to define your class. So this is a second way to do that. Personally, I wouldn't do it like this anymore. What I would do now is, of course, create a lambda function and capture by reference the engine which exists in this context. And that will also pull along the engine into whatever function I pass that distribution to, or that function to rather. So that would be a third way to do the same thing. In the slides, you will actually find 3 consecutive slides, one about bind, one about function objects, so the class approach, which you mentioned, and the third one is about lambda functions. They are sort of interchangeable. The bind is the oldest. Well, no, that's not true. The object-oriented way is the oldest. The bind has been added for convenience. In these sort of situations, it just saves a lot of typing. But the bind approach has been sort of superseded by lambda functions and capturing. So at some point, I will really change this slide and just use lambda function. Anyway, and this is the important part. As you can see, I have generated my distribution, I've generated my engine, and I just call my distribution repeatedly in order to get consecutive random values out of that distribution, or that, let's say, follow that particular distribution. Okay, so that's basically the idea. So clearly, the creation of the distribution and certainly the creation of the random engine is outside of that loop. If you put it inside of the loop, you are getting, point number one, not really random sequences. And second, it is going to be disastrous for performance, since initializing a random number generator, especially an expensive one, time and time again is going to be very expensive. But of course, that is immaterial, since your sequence of random numbers would be gibberish. So don't do that. And I can assure you, I see it a lot. So try not to. Okay. Multiple distributions. So in this particular case, I'm using one engine, but I'm going to use that engine in multiple distributions. So if you use bind, make sure to call std_ref on engine. That is quite important. So the alternative, if you were to use a lambda function, always capture by reference. Why is that the case? Well, suppose that I don't use ref here, then I do a call by value. So C++ runtime is going to copy my random engine. Does that matter? Yes, because then my two distributions are going to use two independent copies of the random number engine. And since those two independent copies have been seeded with the exact same seed, both the result of calling both distributions to get random values will result in pairs of values that are identical. And that is most likely not what I have in mind here, because I'm on the one hand generating x coordinates, on the other hand generate y coordinates. And of course, if they get generated by, at the end of the day, copies of the same initialized random engine, they will be highly correlated. My x and y coordinates will be very correlated. They will actually lie on sort of a line. So that would be really, really bad. So in such a situation, make sure to capture by reference in the context of lambda functions, or to pass by reference, to force a pass by reference if you use bind. Same thing. And obviously, if you use the object-oriented approach, I already mentioned it when I mentioned the constructor. The constructor should take a reference to the random engine. Same reason as here. So the reference is not unique to bind. Here it's made really explicit, but it must be there as well in the object-oriented approach. It must be captured by reference when you use the lambda approach. It's always the same thing in a different guise. But the root cause is, if you pass by value, you copy, you get two highly correlated distributions. Okay. So basically, that's exactly what would happen. The same numbers is of course not quite true, because the distributions are different. For the x, the range is 0 to 1. For y, 0 is 2. So same numbers is not entirely true, but the correlation would be there, and they would lie on the line. Okay. So that was just a little bit about random numbers and what not to do and so on. So basically, it's a little bit different from what you would have in NumPy, because essentially there you draw directly from a distribution. You don't go through a random number generator. Of course, under the hood it's there. Same, no difference. Only you don't see it. Here it's all very explicit, which is nice because it more easily gives you control, which is not nice because it increases typing. Whatever. So it depends on what you want, which is better. Okay, check that out. All right. There is another thing about numerics that I do want to discuss because it's not unimportant. But I don't have a slide on it, so I'll show you some code. Come on, you can do it. At some point, I really have to play with PowerToys in order to get that automated because this is really annoying. Anyway, let's increase the font size a little bit. And let's shift the window a little bit. Okay, now we see everything, I think. Okay. And there is a question somewhere. Let me first go there because I apparently didn't notice it. For real, it's funny, maybe, yeah, okay. Okay, that's interesting. You found that information somewhere on CPP reference about including B? Because I've never heard of it, and as such, as I mentioned, I don't really mind because I'm never going to test on equality for real numbers anyway, so whether it does or not shouldn't really matter for my code. Okay, that's interesting. I never spotted it, so good to know. All right, so let's move on to so this is in the repository, so you have that code or you have access to that code. I did make a number of changes to the repository since last week, but that's in the development branch. So you're not going to notice it in the master branch yet. I still have to do the merge, but I'm in the process of updating a few things and so on. I prefer to be that complete before I do the merge. But if you want the latest and greatest, go to the development branch. There is a bit of new stuff. But as far as I know, this is also in the master branch because I did a merge last week, and this is just a little bit older. So let's have a look at this code. And it's actually a fairly simple problem. It basically just involves the number pi. Okay, so there are many ways in order to get pi in your code. One thing you can do is get a calculator, copy paste, just define a constant. It's one way to do it. Another way to do it is to just compute it on the fly as a constant, of course, as the inverse cosine of -1, for instance. That's also going to give you something that resembles pi. So there are many ways. The better way to do it, though, is to just use a standard template library. And there is this interesting header file here, which is called numbers. And that doesn't do much. So the only thing it does is define a number of mathematical constants. Okay? But there is a bit more to it than that, because otherwise, why would you bother? So let's have a look. Essentially, I'm going to iterate, and I'm going, if memory serves, to compute a sum somewhere. So I have a default value of delta, and I have a sum which is initialized to 0. I'm going to compute the sum of m pi. I'll tell you where m pi comes from in a minute, and then times x. Okay, and x iterates from 0 up to 1 in steps of delta. So this is just essentially adding a lots of pi together. Okay. Notice that this is all floating point, so that's a single precision. That's why it's important that there is a lowercase f here. That means it's a floating point constant. That's C++ way of doing that. Okay. Where is the m pi coming from? Well, that's old style C++. That is a macro. Remember, it's a preprocessor macro. So this is a preprocessor macro, which is defined somewhere in CMOD and gives you some value for pi. So that's what I'm using here. Okay. The start and end thing, this is another part of the standard C++ library, and that allows me to do timings. So basically, the chrono part has to do with time, and I can get now from a high resolution clock. High resolution in this context claims to be nanoseconds. Well, probably not, but okay. It's likely not that precise, but okay. It's high resolution, that's good. So before I start my for loop, I do a timing, I record the time. After I end my loop, I again record the time. And then I can subtract the start time from the end time. And that, of course, gives me a duration. And that is again a type in chrono. Duration, it's parameterized, so it's floating point value, but I want double precision here. And I'm calling that elapsed seconds. Okay, and then I'm going to output that. But note, elapsed seconds is not just a number, it's some object. And the count is actually going to be the number of seconds. Okay, so it seems a little bit weird, but this is a standard way of timing things in C++, just using the standard template library. You need the high resolution thing because the normal clock, I think, is accurate up to a few milliseconds, so that's certainly not good enough for timings. You do want microseconds precision here. Okay, so basically that gives you the time. And then we do a similar thing. There is not much difference here in this loop, except that we use std numbers by value for float. That's the only difference here. So we replace old style m pi with new style parameterized constant. So this is going to give me the value of pi, but in floating point, in single precision. Okay, and basically that's it. We time that again, we compute the duration, and we output that to standard output. Okay. Let's do that. So I can build the software, and let's do the right thing. Oops. CMake build type is release. Basically, that tells CMake, please add compiler options to do optimization. Okay. Doing so generates my build system. Now actually building the software. There are multiple applications there, that's why it takes a while. Okay, done. And now, of course, we can run what was it? Numbers pi versus, yeah, okay, and this one. And I'm going to, well, let's first run it like this. We'll see what it gives and then increase the precision. Okay, as you can see, not much difference. That is pretty much, oh, sorry, I'm looking at the result. Yeah, there is not much difference, hopefully. But as you can see, the time, there is a difference. So basically for mpi, it takes approximately twice as much as for the numbers pi v. Why would that be the case? Because that's weird, I do the same thing. I multiply the same number of x values with pi. I do the same number of additions, and one takes twice as much as the other, twice as much time as the other. Why would that be the case?
You don't know the precision of mpi is, right?
Yes, I don't know what the precision of mpi is. That's correct.
So if that's larger, I don't know how the multiplication will go, but if it goes then to the one with the most significant bits and has to transfer, and then it might take more time because you see, but I don't know if that's the reason, because I don't know what the pi is. So.
Indeed. And that is what you say is okay. We don't know the precision of mpi, so we don't really know what the code is doing. And that's exactly the point. So mpi, if you go and look for it, you will see that it is in fact a double precision constant. Okay, let me go back to the code for a second. No, I don't have it anymore. Let me go back to the slides for a second. So, of course, I have been taking care that everything I do is in single precision. Sum is single precision, x is single precision, and so on. Unfortunately, mpi happens to be double precision. Okay, what's the compiler going to do? The compiler is going to say, okay, I have a multiplication operator with one operand in double precision, with the other operand in single precision. Okay, I have no choice. I have to do that multiplication in double precision, because one of the operands is double precision. So the compiler is going to insert code that turns that single precision x into a double precision x. It's going to do the multiplication in double precision, and then it's going to insert code that converts that double precision result into a single precision number, because that's what I'm supposed to add to sum at the end of the day. So this is called float promotion or double promotion, and that means that without me wanting to, the compiler has actually done what it considers and what is, from a certain perspective, the right thing to do. It's going to preserve as much precision as possible. So it is going to do that intermediate computation, because at the end of the day, multiplication of mpi to x is an intermediate computation. So I might really want that to happen in a higher precision, and then go back to lower precision to do the addition. That would be possible that I want that on purpose. And that's what the compiler is going to do. Of course, that's not my intent in this particular case. What I actually want here is that everything happens in single precision. But due to the fact that I have something here, something unqualified m_p, whatever it is, I have no clue whether that's single precision or double precision. Okay, it's properly stated in the documentation, but still. So basically, I have no control over this. So it's much better to actually use numeric or numbers rather, which allows you to simply specify the type of the constant which you want to have. So there is also an STD numbers pi, and that is also double precision. So if you want a specific precision, you'd have to use the template. Okay, you can say, well, yeah, whatever, but don't forget, if you write your own templates, then this could be a type parameter, and that should be consistent with the rest of your computation. So that's the added value of having these numbers. And we can have a look at what is defined there. So obviously pi, that's pretty clear, but there is quite a number of other mathematical constants that are interesting. They are listed here, mathematical constants. And as you can see, there is the value of e. There is the logarithm of e in base 2, in base 10. There is pi, the inverse of pi. Interesting. That's something that you regularly need. Okay, is pre-computed for you to the appropriate precision. So this doesn't happen at runtime. This happens at compile time. Well, that's pretty nice. Inverse square root is also something that of pi. That's also something that I used quite a lot back in my statistical physics days. Logarithm of 2, etc., etc. So that would be the natural logarithm of 2, the natural logarithm of 10, the square root of 2. Again, something I used a lot, etc., etc., etc. Also 5 for the Goblin ratio and so on. And then you have the same thing, but simply specified in double precision. So the constants named by themselves without the template will be double precision. If you want to parameterize that with a type, you can do that with the _v suffix and then specifying the underlying type. And you will get the right thing. I mean, you will get a precise value for these constants, either in float or in double. So I would very much recommend to use this because other things will work, but they might inadvertently slow you down, and they might also not be to the precision which you would expect. Because, okay, I didn't bother to compare the inverse cosine of -1 with this value, but I'm pretty sure it's not really identical, unless they hacked something somewhere to get the right value, but otherwise it's not going to be the exact value. So I'd really recommend to have a look at this module. I have to add a slide at some point because this is not unimportant and something that's easily overlooked. Okay, let's talk a little bit about linear algebra. There are a million libraries to do linear algebra. Okay, no, there are at least 5 that I know of for C++ alone. So I've chosen a few here because I rather like them, but there are different ones. Principles are typically similar, let's put it that way, except for the very sophisticated ones, but yeah, then you'll only benefit when you do parallel programming. That's a bit out of scope here, so I limit myself to the standard things, or to the more sequential stuff. Okay, so for me there are 2 nice ones. One is Eigen, and the other is Armadillo. So Eigen is very much template based, so in that it fits in quite well in the spirit of C++. Armadillo is also based on templates, but to maybe somewhat lesser extent. An advantage of Eigen is that you can install it trivially because it's a header-only library. So it can operate without any external libraries, only the source code of the Eigen headers. That's a benefit because it's easy to install. You just drop in all the header files, you make sure that your compiler finds them, you're done. Compiler is going to generate code for you. So that's great, except that you don't get any performance. Because what you want to do, of course, is to make sure that Eigen itself calls into BLAS. So the basic linear algebra subroutines, which is a standard of which there are a number of good implementations. One good implementation is OpenBLAS, that's open source software. The other implementation is, which is certainly good, is Intel MKL, so the not kernel library, which comes with one API. So basically, you can now use it for free. And this is very good quality, so make sure that if you install Eigen, it's not just a header only, because then you will regret it. For prototyping, it's nice. For small things, it's nice. For something numerical intensive, nah, I don't think so. So don't do that, then do a proper install so that it links against BLAS and LAPACK linear algebra package, which would give you, okay, let me, maybe, for those of you who are not aware, so BLAS gives you vector operations, things like scale a vector by a certain number, compute the norm of a vector, that kind of pretty boring stuff. Matrix vector operations, so for instance multiplication of a matrix with a vector, and matrix-matrix multiplications. And this for various special types of arrays, of matrices, let's put it that way. Diagonal matrices, banded matrices, etc., triangular matrices. So there are special implementations for each of those types of matrices in order to speed things up when you do linear algebra. So what you will find there is solving a set of equations given that's in triangular form. Okay, that's not really convenient. So it doesn't do linear algebra in the broad sense. It's just a very basic core of matrix operations. That's what it does, and that's what it does well. So OpenBLAS, for instance, is parallelized. If you run it on a CPU with multiple cores, it's happily going to use all these cores, speeding up your computations potentially by an interesting factor. So if you need more linear algebra, so if you need to solve arbitrary sets of linear equations, if you want to do linear regression, if you want to do matrix decompositions, singular value decomposition, QR decomposition, whatever, then LAPACK will be your friend. And under the hood, LAPACK is using BLAS. So that's how these things tie together. And then typically, if you have something like Armadillo, that is going to be a wrapper around these things, and maybe some extensions and so on, but it's going to use, at the core, it's going to use BLAS. And similar for Eigen. And similar for any self-respecting linear algebra library. By the way, similar for NumPy. It's also going to use BLAS under the hood if you install it properly. Okay, if you don't, you're going to regret it quite a lot. Anyway, Armadillo is an alternative. So this requires BLAS and LAPACK to be installed. So that's a prerequisite. So you have to make sure that you've got it on the system. Of course, on any HPC system, you've got them via modules. It's, in my opinion, quite convenient. It gives you quite reasonable performance. A potential drawback is that you don't have any distributed algorithms. So that is not something that Armadillo is going to do for you. If you want something like that, you would either use MKL directly or LAPACK, scale LAPACK directly, depending on your open source or not so open source approach, or any of the other libraries. You have Magma, for instance. You have linear algebra libraries that allow you to do heterogeneous programming, so that can offload certain computations to the GPU while doing others on the CPU and so on. So there are quite a number of libraries out there that support that kind of thing. Okay, that's out of scope. So basically, I'll just briefly show a little bit what Armadillo looks like. The bottom line of the whole thing is, don't implement this yourself unless you're doing research into linear algebra for new algorithms, because you're never ever going to match a good implementation. Writing your own matrix-matrix multiplication, that's a good exercise for programming 101, but after that, never do it again. Okay, so bottom line, or not bottom line, but just showing you. Basically, I'm using namespace Arma here, so that I don't have to prefix everything with that name scale. Okay, so I have two types of vectors, column vectors and row vectors. And then I can specify a type. So that can be integer, that can be real. It can be single precision, double precision, whatever. And I have a few shortcuts like colvec and rowvec, and that's just double precision. And vec, again, is a shortcut for a column vector, whatever. Similar for matrices. So mat is simply a double precision matrix. SP mat is a sparse matrix. So you have dense matrices, sparse matrices, so that's already nice. That means that if you deal with arrays that are mostly zeros, you likely want to encode that not as a dense matrix where all elements are stored, but rather as a sparse representation where you only store the non-zero values and the positions where they occur. Okay, so essentially what you need to keep in mind that the type needs to be scalar. So it needs to be something numeric. Integers, real numbers, complex, whatever, but you can't have a matrix consisting of matrices. So Armadillo does not support that, and of course in the context of linear algebra that would make absolutely zero sense. So they just don't do that. And you also have cubes and three-dimensional arrays. Okay, there are fields, so basically you can create 2D or 3D arrays of arbitrary objects. So it does exist, but of course that's not something typically you do linear algebra on. But they do support that data type, not as matrix, but as a different type, which is a field. And then object type can be anything you like. Okay. You can literally assign, so basically this would be a vector with two elements, and it's going to be double precision, and it's going to be a column vector. A is specified as what I would call a list of lists. So the first curly bracket denotes the first row, the second curly brackets denote the second row. Okay. So that would give me matrix A with 2 rows, 3 columns. Okay. The linspace function will sound familiar to those who are, on the one hand, familiar with Fortran, MATLAB, or NumPy. Yeah. And basically, it sort of works the same way. You specify the minimum value, the maximum value, and the number of values you want. And you also specify the result type, which in this case is just, again, double precision, column vector. So quite simple. Then regular space here. So, basically you specify a start value, you specify an end value, and you specify delta. So this would resemble NumPy's arrange, while linspace would be the equivalent of, linspace. You can also generate matrices. For instance, the identity matrix 5 by 5. I means identity matrix. This is a dense matrix with double precision numbers. 5 rows, 5 columns. Here, for instance, a random matrix, matrix of random elements, normally distributed, and it would be a 2 by 3 matrix. A column vector with normal distribution, zeros, so a column vector again with 10 elements all set to 0. A matrix, 3 rows, 2 columns, all set to 1. So again, if this resembles MATLAB or NumPy, that's obviously not a coincidence. Okay, so matrix arithmetic is done by operator overloading. So basically I've got two arrays A and B, and I can compute vector V, and I can compute expressions such as this. Now, if you're very smart with templates and very smart with operating overloading, then you can actually ensure that if this thing is compiled, you don't generate extra temporary matrices. Remember what I told you about temporary matrices, 3 times A plus 5 times B? You can be very smart as a programmer and avoid that by using templates. So the good linear algebra C++ implementations will actually do that for you. But that's up to not to the compiler, that's up to the person who overloads the operators. That this is done in such a way that you get element-wise behavior all through without ever creating a template. Okay, then here's another example. So basically non-dot. So that would not only compute the inner product between those two matrices, so the scalar product, but also do the normalization. And then there are quite a number of operators. Basically everything you would expect. Determinant, the actual just dot product, etc. etc. Okay. Matrix access is done by round brackets. And that might seem very weird. That's a C++ thing. So, for whatever reason, I have no idea why this historically is the case, but it is the case. Up to C++ 23, you cannot overload the square bracket operator with a function that takes more than one argument. That just does not compile, literally. Compiler refuses to do it because the C++ standard says you can't. Okay? C++ standard was changed. It's changed in order to allow this, but only starting from C++ 23. And frankly, I didn't check whether it's implemented yet. I don't know. But you won't find it in any, let's say, library that wants to be backward compatible, because that's a major change. It's a very good change. I'm very happy with it. But yeah, if I were maintaining a library, I wouldn't switch anytime soon. Because again, that would mean that if people use older compilers, they can't compile and hence use my library. That's bad for my citation index. So I'm not going to do that. Okay, so round brackets. Okay, that's what it is. What you need to remember is that elements are stored column-wise. So similar to MATLAB, Fortran, Julia, R, etc., etc. Contrary to NumPy. Contrary to native two-dimensional arrays in C++. So that's a little bit different and a little bit unexpected given C++'s inheritance and so on. Makes sense because, of course, many of the underlying libraries like BLAS and LAPACK were originally designed for Fortran and hence have everything in column-meter order stored. So it does make sense. Okay. And then you have similar things like in the standard template library, like for instance a transform function, and you can just do any transformation with an element of an array. So that would be in place. Okay, so some linear algebra, basically signal value decomposition. So essentially it's you pass the out arguments in this case. So U, S, and V will be populated by the SVD function. You have something like diag matrix, which constructs a diagonal matrix out of a vector. And then you can just do the matrix multiplication. The T here is the transpose, so it's pretty natural. What you write is pretty natural. Okay. Matrix inverse is just A dot I. Okay. All right. Maybe very briefly a look at eigen, so the contender, let's put it that way. And let's not do boost right now. So eigen has actually its own directory. And for instance, let's do something, solve equations. That looks like an interesting example. CPP, where are these executable here? Anyway, so basically, this is more C++. Because, for instance, the way to initialize a matrix is using the send-to operator. So it has overloaded the send-to operator to initialize the matrix. I do have to specify the dimensions, so the number of rows and the number of columns, but then I can just use the send-to in order to populate, to initialize the elements of my matrix. So it's a different approach, but yeah, okay. And then also the send-to operator has also been overloaded to send a matrix to some out. And it will show it row by row, elements separated by spaces. Okay, so this would be a double precision matrix. I know that because there is a D here. And here this is a vector, again double precision due to the D, with two components. And again, I can just use the send-to operator in order to initialize it. Same thing, sending it to standard input is very easy. Okay, so I want to do a decomposition. So I'm going to do a partial LU pivot of A, store that in decomposition. Then I define X, and that's actually solving the equation AX is B. So B is the right-hand side of the equation. A is the coefficients of the variables, the known variables. And so X will be populated by the solution of solving A, X is equal to B. So the advantage of this approach, because it's a two-step thing, is of course that if I want to solve many equations which are the same except for their right-hand side, I only have to do the LU decomposition once, and then I can benefit from that time and time again by supplying different instances of the right-hand side of my set of linear equations. Okay, and then we just print A, and we can just do some matrix arithmetic here, just as we could do in Armadillo. So as you can see, there are quite some similarities. Type names are different. Initialization is different. In a way, a bit more sophisticated in eigen. So they do sort of the same thing, but they have chosen different paths. Let's put it that way, design paths. But both are nice. I like working with both of them, so it's quite reasonable. I didn't do an in-depth comparison here with respect to performance. Would be interesting to do, but I didn't do that. Okay, let's stop here for today and see you tomorrow for the last part. And then we'll start talking about something that's always annoying the hell out of C++ programmers, which is move semantics versus copy semantics, and the rule of 5 and the rule of 0 and all that kind of thing. So that will be pretty technical with respect to C++. Okay. If there are no more questions, then we conclude here for today.
Right.
See you tomorrow. See you.